Look up at the night sky. What do you see? Pinpricks of light, a serene darkness, a quiet emptiness. It's a view that feels still, almost peaceful, but that is the greatest illusion of all. The truth is, the cosmos is never still. It is a stage for a performance of unimaginable scale, a grand ballet where stars are the dancers and galaxies are the swirling ensembles. And every single movement, every spin, every orbit is guided by invisible hands. These are the unseen forces of the universe, the hidden conductors of the celestial dance. We are about to pull back the curtain on 25 of these profound powers, from the cosmic push of dark energy to the subtle thermal nudges that steer asteroids. This journey will reveal that what we perceive as the serene mechanics of space is actually a dynamic, often violent, and always intricate interplay of influences that remain, for the most part, completely hidden from our eyes. This is not a story just for scientists with powerful telescopes. This is a story for anyone who has ever felt a sense of wonder while gazing at the stars. It's about understanding the fundamental rules written into the fabric of reality itself, rules that govern everything from the path of the moon above your head to the ultimate fate of the entire universe. To know these forces is to learn the language of the cosmos, to see the invisible threads that connect us to the most distant galaxies. Think about the simple act of a planet orbiting a star. We learn in school that gravity is the reason, and we leave it at that. But what is gravity? Is it just a pull? The real answer is far more strange and beautiful. It is a curvature in the very fabric of spacetime, a warp created by mass, like a heavy ball resting on a stretched rubber sheet. This single force, so familiar to us, holds profound mysteries that even Einstein's genius only began to unravel. And gravity is just the beginning, the most recognizable face in a crowd of invisible giants. There are forces at work that defy our basic senses. There is matter that does not interact with light, yet its gravitational grip is so strong it holds entire galaxies together. There is an energy, a repulsive pressure inherent to the vacuum of space itself, that is causing the entire universe to expand at an ever-increasing rate, a discovery that overturned our deepest assumptions about cosmic fate. This exploration will take us from the quantum ripples in the first moments of the Big Bang, which seeded all the structure we see today, to the gravitational waves sent out by colliding black holes, ripples in spacetime that we can now detect here on Earth. We will see how magnetic fields, invisible lines of force, channel cosmic rays and shape the birth of stars. We will understand how the spin of a planet can dictate the formation of a hurricane, and how that same principle, scaled up to galactic proportions, helps sculpt magnificent spiral arms. Each of these 25 forces is a verse in a cosmic symphony, and together they choreograph the grand dance of celestial bodies. By the end of this video, your perspective on the night sky will be transformed. You will not see a silent void, but a dynamic arena filled with invisible activity. You will understand that the universe is a place of constant, orchestrated motion, and we are about to decode the secrets of its silent conductors. Prepare to see the stars not as distant lights, but as partners in a dance guided by forces more incredible than you have ever imagined. Of all the invisible hands guiding the cosmos, there is one we feel every single day, a force so familiar we often take its profound mystery for granted: gravity. It is the anchor of our reality, the reason we are held to the Earth, and the reason the Earth is held in its graceful loop around the Sun. For centuries, we understood it simply as a pull, an attraction between objects with mass. But then came Albert Einstein, and with his theory of general relativity, our understanding was utterly transformed. Einstein proposed that gravity is not a force in the traditional sense, not some mysterious tugging across empty space. Instead, he envisioned space and time as a single, flexible fabric called spacetime, and mass, he said, warps this fabric. Think of a taut, stretched rubber sheet. Place a heavy bowling ball in the center and it creates a deep, curved depression. Now roll a marble across the sheet. Instead of traveling in a straight line, the marble will curve, spiraling inward toward the bowling ball. The marble isn't being pulled by a magic string. It's simply following the curvature of the sheet. This is the essence of gravity. The sun is our cosmic bowling ball, creating a vast gravitational well in the space-time of our solar system. The planets are the marbles, their orbits simply the paths they follow as they roll along the curved geometry of space created by the sun's immense mass. This curvature dictates everything from the orbit of a tiny moon to the majestic dance of binary stars. But gravity's influence stretches far beyond orbital mechanics. It is the cosmic glue that binds entire galaxies together, preventing billions of stars from flying off into the void. It gathers vast clouds of gas and dust, compressing them until they ignite into new stars. And in one of its most mind-bending effects, gravity influences the very flow of time itself. The closer you are to a massive object, the stronger the gravitational field, and the more time actually slows down relative to a weaker gravitational field. This isn't science fiction. It's a measured effect known as time dilation, crucial for the accuracy of GPS satellites orbiting high above the Earth. So, while gravity is the force we know best, it is also a gateway to the deepest mysteries of the universe, a foundation upon which all the other unseen forces we will explore begin to build their complex and beautiful choreography. But if gravity, as we understand it, is the conductor of the cosmic orchestra, then we must confront a stunning mystery. The music we observe simply does not match the number of musicians we can see on the stage. This brings us to our first and perhaps most profound unseen force, the ghostly grip of dark matter. Imagine a presence that is everywhere, that exerts a powerful gravitational pull, yet is completely undetectable by any telescope ever built. Dark matter is exactly that, a form of matter that does not emit, absorb, or reflect a single photon of light. It is utterly transparent, completely invisible across the entire electromagnetic spectrum. We cannot see it, but we can see what it does, and its influence is absolutely undeniable. The story of its discovery begins not in the vast emptiness between galaxies, but within them. In the 1930s, a brilliant astronomer named Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies. He measured how fast these galaxies were orbiting the cluster's center. The speeds were staggering, so high that, according to the laws of gravity and the amount of visible mass, all the stars and gas he could see, the entire cluster should have flown apart long ago. It was as if the galaxies were being held together by an invisible glue, a tremendous amount of mass that was simply missing from his observations. Zwicky called this missing mass dunkel materie, or dark matter. For decades, this was considered a curious anomaly, but the case became airtight in the 1970s with the work of astronomer Vera Rubin. She meticulously mapped the rotation speeds of stars within individual spiral galaxies. Everyone expected that stars farther from the galaxy's bright center, where there are fewer visible stars, would orbit more slowly, just as Pluto orbits the Sun more slowly than Earth does. But that's not what she found. To everyone's astonishment, the stars at the outer edges of galaxies were orbiting just as fast as those near the center. The only possible explanation was that each galaxy is embedded within a gigantic, invisible sphere of matter, a halo that extends far beyond the visible edge of the galaxy. This dark matter halo provides the extra gravitational pull to keep those high-speed outer stars from being flung out into intergalactic space. We now understand that dark matter is not a minor component of the universe. It is the dominant architecture. It acts as a cosmic scaffold, an unseen framework upon which the visible universe is built. After the Big Bang, it was the gravitational pull of dark matter that first gathered ordinary matter. The protons, neutrons, and electrons that make up everything we see into the dense clouds that would eventually collapse to form galaxies and clusters of galaxies. Without this dark matter framework, the universe would be a much more diffuse and barren place, with stars and galaxies struggling to ever form. Think of it like this. If the luminous stars and glowing gas of a galaxy are the glittering lights of a city seen from an airplane at night, then dark matter is the entire continent, the massive landmass upon which that city is built. We only see the pinpricks of light, but the vast underlying structure is what truly defines the landscape. This silent, invisible partner in the gravitational dance doesn't just influence local motions. It shapes the large-scale structure of the entire cosmos, weaving the great cosmic web of filaments and voids that defines the universe on the grandest of scales. But just as we begin to comprehend the immense pulling power of dark matter's ghostly grip, we encounter a force that operates on an even grander and more bewildering scale, a force that does the exact opposite. If dark matter is the universe's ultimate anchor, then our second unseen force, dark energy, is its cosmic accelerator, an enigmatic push that is stretching the very fabric of the cosmos at an ever-increasing rate. For most of the 20th century, cosmologists were locked in a debate about the ultimate fate of the universe. Would the collective gravitational pull of all matter eventually halt the expansion from the Big Bang and cause a big crunch, a cosmic collapse, or would the universe continue to expand forever, gradually slowing to a near standstill? The prevailing assumption was that gravity, as an attractive force, would act as a brake, causing the expansion to continuously slow down over billions of years. It was a logical conclusion. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it would win them the Nobel Prize and fundamentally rewrite the story of our cosmos. They were observing a specific type of stellar explosion known as a Type Ia supernova. These events are crucial because they act as standard candles. They have a known, predictable intrinsic brightness. By measuring how bright they appear from Earth, astronomers can calculate their distance with great accuracy. Furthermore, by analyzing the redshift of their light, they can determine how much the universe has stretched since the explosion occurred. When these teams looked at supernova in extremely distant galaxies, meaning they were looking back in time billions of years, they expected to find that the expansion was slower in the past than it is today. But the data revealed the impossible opposite. The distant supernova were fainter than expected, indicating that they were farther away than the standard model of a slowing expansion could explain. The only possible conclusion was that the expansion of the universe is not slowing down at all. It is speeding up. Something is actively working against gravity's pull, pushing galaxies apart with a kind of anti-gravity force. This something was named dark energy, so what could it be? The leading explanation points back to an idea even Einstein once considered and then discarded, the cosmological constant. This suggests that dark energy is a property of space itself. According to quantum physics, empty space is not truly empty. It seethes with virtual particles that flicker in and out of existence. This vacuum energy generates a repulsive pressure, a kind of negative gravity that causes spacetime itself to expand. The more space there is, the more of this repulsive energy is created. leading to a runaway effect of faster and faster expansion. Imagine blowing up a balloon with a very special property. The rubber itself actively wants to expand. The more you inflate it, the stronger this intrinsic desire to stretch becomes. Our universe is that balloon, and dark energy is that mysterious property of the rubber. This force ensures the cosmic dance is not a slow, graceful waltz winding down, but a frantic, accelerating spectacle where the dance floor itself is stretching at an ever-increasing pace, pulling the dancers, the galaxies, further and further apart. While dark matter works on the scale of galaxies, sculpting local structure, dark energy operates on the largest canvas imaginable, dictating the ultimate fate of the entire universe. Now we shift our focus from the immense gravitational forces shaping the cosmos to another, equally powerful but very different kind of influence, the invisible architecture of magnetic fields. While gravity warps the very stage of spacetime, magnetism creates a complex web of lines and channels that guide and constrain the movement of charged particles throughout the universe. These fields are not solid structures, of course, but rather regions of influence, invisible pathways generated by the motion of electric charges. Anytime charged particles like electrons and protons move, whether deep within a planet's core or in the turbulent plasma of a star, they generate a magnetic field. This means our own Earth has a powerful magnetic field generated by the churning motion of molten iron in its outer core. The Sun, a colossal ball of charged gas, has a magnetic field that is both incredibly complex and dynamic. Even the vast, seemingly empty spaces between stars are threaded with faint but extensive magnetic fields, woven through the interstellar medium. The power of these invisible lines becomes clear when we see how they shape cosmic events. Take the process of star formation. A giant cloud of gas and dust begins to collapse under its own gravity. As it contracts, any weak magnetic field threading through the cloud becomes amplified and concentrated. This magnetic field exerts a pressure that can resist the gravitational collapse, effectively putting the birth of a star on pause. It's only through a slow process called magnetic diffusion, where the neutral particles slip past the magnetic field lines, that the cloud can continue to collapse and finally ignite. In this way, magnetic fields act as a cosmic regulator, controlling the pace at which new stars are born. They also channel high-energy particles, cosmic rays, which are atomic nuclei accelerated to nearly the speed of light, do not travel in straight lines across the galaxy. Instead, they spiral along the invisible pathways of interstellar magnetic fields, their paths bent and twisted as if they were following a complex network of interstellar railways. Perhaps the most beautiful and direct evidence of magnetic fields at work is the aurora. Here on Earth, we call them the northern and southern lights. This stunning light show begins 93 million miles away with the Sun. Our Sun is constantly boiling, and its churning plasma generates a powerful and tangled magnetic field. When these field lines become too twisted, they can snap and reorganize in a violent event known as a solar flare or a coronal mass ejection, hurling billions of tons of charged particles out into space. This stream of particles, the solar wind, carries the Sun's magnetic field with it across the solar system. When this wind reaches Earth, it interacts with our planet's own magnetic field, which acts like a protective shield. Most of the particles are deflected, but some are funneled down along the magnetic field lines toward the north and south poles. There, they collide with atoms in our upper atmosphere, transferring energy and causing them to glow in those magnificent, shimmering curtains of green and red light. The aurora is a direct manifestation of an invisible force, a spectacular light show orchestrated by magnetic fields connecting the Sun to our sky. The Sun's magnetic influence doesn't stop at creating auroras. Its magnetic field is the engine for all space weather. The solar wind, a constant outflow of charged particles, carves out a vast bubble in the interstellar medium called the heliosphere, which envelops our entire solar system. Within this bubble, the Sun's magnetic field dictates the environment for every planet. It drives the intense heating of the Sun's corona to millions of degrees, a mystery that has puzzled scientists for decades. It creates sunspots, those temporary dark patches on the Sun's surface that are actually regions of intense magnetic activity. And when solar storms are particularly powerful, they can disrupt satellites, affect power grids on Earth, and pose a radiation risk to astronauts. So while we cannot see these magnetic lines with our eyes, their effects are felt profoundly, demonstrating that the space between planets is not an empty void but a dynamic medium shaped by forces that, while unseen, are fundamental to the story of our solar system and the galaxy beyond. Now let's turn our attention to a force that feels almost like an illusion, a trick of perspective born from motion itself. This is the Coriolis effect, a subtle twist that arises not from a direct push or pull, but as a direct consequence of living on a rotating body. Picture yourself standing at the center of a perfectly smooth, rotating merry-go-round. If you try to roll a ball straight outwards to a friend standing on the edge, something strange happens. From your perspective, you rolled it perfectly straight, but from the viewpoint of someone watching from a stationary point above, the ball appears to curve. This isn't because a mysterious force pushed it. It's because while the ball was in the air, your friend on the edge moved as the merry-go-round turned. The ball's path appears to deflect because the reference frame, the merry-go-round, is spinning beneath it. This apparent deflection is the heart of the Coriolis effect. It's crucial to understand it's not a true force like gravity or magnetism. It's an inertial or fictitious force that we must account for because we are observing motion from within a rotating system. We see this effect play out on a grand scale right here on Earth, most dramatically in the atmosphere. As large air masses move from high-pressure areas to low-pressure areas, they are deflected by our planet's rotation. In the northern hemisphere, this deflection is to the right of the direction of travel. In the southern hemisphere, it's to the left. This is why hurricanes and cyclones spin in opposite directions depending on which hemisphere they form in. In the North Atlantic, a hurricane is a massive, swirling vortex spinning counterclockwise. The low-pressure center acts like a drain, pulling air inward, but the Coriolis effect deflects that rushing air, setting the entire system into a spinning motion that can grow into a devastating storm. It's the spin of our planet, an unseen rotation we cannot feel, that imprints this distinctive spiral pattern onto our weather systems, a constant reminder that we are living on a moving platform. But the influence of this rotational twist doesn't stop at the edge of our atmosphere. We can scale this principle up to galactic proportions, where it helps to solve one of astronomy's most beautiful puzzles, the majestic spiral arms of galaxies. Our own Milky Way is a classic spiral galaxy, with long, curving arms filled with bright, young stars and glowing gas clouds. For a long time, a major question persisted. How do these spiral arms maintain their shape over billions of years? If they were simple, fixed structures of stars orbiting the galactic center, the galaxy's differential rotation, where stars closer to the center orbit much faster than those farther out, would quickly wind them up so tightly they would disappear within a few orbits. The arms should have wound themselves up eons ago. The solution is a concept called a density wave, and the Coriolis effect plays a key role in its behavior. Think of a spiral arm not as a permanent lane of stars, but more like a traffic jam on a circular highway. The cars themselves are the stars and gas clouds. They continuously move into the jam, slow down while they're in it, and then move out the other side. The traffic jam itself, the region of higher density, moves around the galaxy at a different, slower speed than the individual cars. The Coriolis effect helps to orchestrate this cosmic traffic flow. As a cloud of gas enters the denser region of a spiral arm, the increased gravitational pull compresses it, triggering the collapse that leads to star formation. The Coriolis effect, acting on the motions within that cloud, influences how it spins and collapses, contributing to the overall pattern. This grand, rotating dance, governed by the same apparent deflection we see in a hurricane, ensures that the spiral arms are not static structures but persistent patterns, rotating waves of creation that give spiral galaxies their iconic and enduring form. We often think of gravity as a simple, uniform pull, a force that draws objects together as if connected by an invisible string. But the true nature of gravity is far more nuanced and, in some ways, more violent. This brings us to our fifth unseen force, the stretching, sculpting power of tidal forces. The key to understanding tidal forces lies not in gravity's absolute strength, but in its gradient, the difference in its pull from one point to another. Because gravity weakens with distance, the side of an object closer to a massive body feels a stronger tug than the side farther away. It is this difference, this stretching force across the object, that creates the tidal effect. The most familiar example is right here on Earth with our ocean tides. The moon's gravity pulls on our planet. The ocean water on the side of Earth facing the moon is pulled most strongly, creating a bulge. You might expect the opposite side to have a low tide, but something more interesting happens. The Earth itself is also pulled more strongly than the water on the far side, so the planet is, in effect, pulled away from that far side ocean water, leaving it behind as a second bulge. So, Earth has two tidal bulges, one where the water is pulled toward the moon, and another where the water is essentially left behind. As Earth rotates daily beneath these bulges, any given coastline experiences two high tides and two low tides roughly every 24 hours. The Sun contributes to this effect as well, with its immense gravity either enhancing the moon's tide during a full or new moon, creating spring tides, or partially cancelling it out during quarter moons, creating neap tides. This daily rhythm, so crucial to coastal life, is a direct and gentle manifestation of gravity's gradient, but tidal forces can create much more permanent and dramatic arrangements. Consider tidal locking, a state achieved by many moons in our solar system, including our own. The moon always shows the same face to Earth. This isn't a coincidence, it's the result of tidal forces over billions of years. The Earth's gravity created a slight, elongated bulge on the moon when it was still molten and flexible. As the moon rotated, Earth's gravity constantly tugged on this bulge, acting like a brake until the moon's rotation period perfectly matched its orbital period. Now, it takes the same amount of time to spin once on its axis as it does to orbit Earth once, so one hemisphere is forever pointed toward us. This same process has locked Mercury in a 3:2 resonance with the Sun, and it's why Jupiter's large moons, like Europa and Io, also present the same face to their giant planet. Tidal forces have synchronized their spins with their orbits, creating a cosmic choreography of captured rotation. The most extreme expression of tidal forces, however, is one of the most violent events in the universe, tidal disruption. When a star wanders too close to a supermassive black hole, the difference in gravity's pull becomes catastrophic. The side of the star nearest the black hole is pulled with exponentially more force than the far side. This tidal gradient overwhelms the star's own gravity, the force that holds it together. The star is literally stretched into a long, thin stream of gas in a process picturesquely known as spaghettification. This stream of stellar material then wraps around the black hole, feeding a brilliant, short-lived accretion disk that can outshine an entire galaxy for a brief period. Astronomers have witnessed these tidal disruption events, seeing a distant galaxy suddenly flare with incredible intensity as a star is torn apart. This demonstrates that gravity is not always a gentle anchor. It can also be a destructive sculptor, capable of ripping apart a sun with nothing more than the subtle difference in its pull from one side to the other. From the gentle rise and fall of our oceans to the locked faces of moons and the utter destruction of stars, tidal forces reveal gravity not as a simple pull, but as a complex and powerful shaper of cosmic bodies. We've explored how gravity warps the stage of spacetime and how magnetic fields create invisible pathways. But now we encounter a force that seems almost paradoxical, one that originates from the very essence of light itself. Light is energy, a wave, a particle, but can it be a push? The answer is a definitive yes, and this brings us to our sixth unseen force, the subtle but significant push of radiation pressure. It's a concept that challenges our intuition because we're taught that to exert a force, to push something, you need mass. Yet photons, the fundamental particles of light, have precisely zero mass. How can something with no mass push against matter? The secret lies in a cornerstone of physics. Photons may be massless, but they carry momentum. Think of momentum not just as a property of moving objects with mass, but as a fundamental quantity of motion in the universe. When a photon strikes a surface, it transfers its tiny amount of momentum to that surface, imparting a minuscule push. Individually, this push is incredibly weak, utterly undetectable to our senses. But when you gather the sheer, staggering number of photons streaming from a source like the Sun, that collective push becomes a powerful force that actively shapes cosmic events. This photonic push plays a starring role in the life cycle of stars, acting as a crucial balancing force against the relentless crush of gravity. Inside a star like our Sun, a titanic battle is constantly raging. Gravity pulls inward, trying to compress the star into an ever smaller, denser ball. Meanwhile, the furious nuclear fusion in the core generates an immense outpouring of light, a flood of photons pushing outward. In a stable, main-sequence star, these two forces achieve a perfect, long-lasting equilibrium. The outward pressure from radiation exactly balances the inward pull of gravity. This balance is what defines a star's size and stability for billions of years. It's a delicate standoff where light itself acts as a supporting pillar, preventing the star from collapsing under its own weight. Without this constant outward push from the light it creates, a star would swiftly implode. But for the most massive stars, the story is even more dramatic. These stellar giants burn their nuclear fuel with such ferocious intensity that the outward pressure of radiation becomes truly dominant. The flood of photons leaving the core is so intense that it doesn't just support the star, it begins to violently push on the outer layers of the star's atmosphere. This radiation pressure becomes so powerful that it drives a continuous, powerful stellar wind, ejecting massive amounts of material into space at incredible speeds. In the most extreme cases, this radiation-driven wind can be so strong that it literally blows the star apart, contributing to spectacular supernova explosions or creating luminous blue variable stars that undergo giant eruptions. Here, the gentle push of light transforms into a stellar hurricane, sculpting the environment around the star and seeding the galaxy with the heavy elements forged in its core. The faint sunlight that warms your skin is a gentle reminder of this same force operating on a cosmic scale, a force that governs the birth, life, and death of the very stars that light the universe. The promise of radiation pressure isn't confined to distant stars. it offers a visionary pathway for our own exploration of the cosmos. This is the principle behind the concept of a light sail or solar sail. Imagine a spacecraft that needs no traditional rocket fuel. Instead, it deploys a gigantic, ultra-thin, and highly reflective sail, perhaps miles across. Photons from the Sun, each delivering their tiny push, would collectively strike this sail and transfer their momentum, gradually accelerating the spacecraft. There would be no fiery exhaust, only a silent, continuous acceleration. While the push from sunlight is gentle, it is also constant. Over time, a solar sail-powered probe could reach tremendous speeds, potentially journeying to other stars within a human lifetime. We've already seen successful tests of this technology. The Japanese Ikaro's mission proved that solar sailing is viable, and projects like Breakthrough Starshot aim to use powerful Earth-based lasers to push tiny, wafer-thin probes to a significant fraction of the speed of light, sending them to our nearest stellar neighbor, Proxima Centauri. This demonstrates that radiation pressure is not just an abstract astronomical concept. It is a tangible force that could one day propel humanity into the interstellar age, turning the gentle pressure of light into the engine for our greatest voyages. The gentle pressure of sunlight is just one part of the Sun's constant conversation with the solar system, for alongside that stream of photons flows a far more material river, a relentless gale of charged particles that constitutes our seventh unseen force, the solar wind. This isn't a gentle breeze, it's a supersonic plasma storm, a stream of mostly protons and electrons boiling off the Sun's superheated outer atmosphere, the corona, and racing outward in all directions at speeds of hundreds of kilometers per second. The existence of this wind was first theorized to explain why a comet's tail always points away from the Sun, regardless of the comet's direction of travel. It wasn't pushed by light alone, but by a tangible, particle-laden stream. This constant, invisible outflow is the Sun's most active and direct influence on the planets, a force that carves out a sovereign territory for our solar system in the galaxy. The most significant creation of the solar wind is a vast protective bubble known as the heliosphere. Imagine the Sun moving through the galaxy like a ship plowing through the ocean. The solar wind is the exhaust from its engines, pushing against the interstellar medium, the thin soup of gas and dust that fills the space between stars. The point where the pressure of the outgoing solar wind finally balances against the pressure of the incoming interstellar material is the boundary of the heliosphere. This bubble acts as a crucial shield for every world within it, deflecting a significant portion of dangerous interstellar cosmic radiation. These high-energy particles, originating from distant supernova and other violent cosmic events, are mostly stopped at the heliopause, the outer edge of this protective envelope. Without this invisible barrier generated by the Sun's constant exhalation, the radiation environment within our solar system would be far more hostile, potentially impacting the development of life itself. We are, in a very real sense, living inside a giant protective cavity blown by the solar wind. When this wind reaches the planets, its interaction defines their very character. For a world like Earth with a strong global magnetic field, the encounter is dramatic. Our magnetic field acts as a formidable obstacle, standing against the solar wind like a rock in a river. The wind cannot penetrate the field directly. Instead, it compresses the field on the side facing the Sun and stretches it into a long, comet-like tail on the night side, creating a protective region called the magnetosphere. Most of the solar wind's particles are deflected around this magnetic shield, flowing harmlessly past our planet. Some, however, become trapped in vast, donut-shaped radiation belts, while others are funneled down to the poles to create the auroras. This magnetic defense system is our primary protection, preserving our atmosphere and making the surface a safe haven. The fate of a planet without this magnetic shield tells a very different story, and it's written across the barren, rust-colored surface of Mars. Billions of years ago, Mars was a warmer, wetter world with a thicker atmosphere and likely even flowing water on its surface. But Mars is a smaller planet, and its interior cooled relatively quickly, causing its global magnetic dynamo to shut down. Without a planet-wide magnetic field to stand against the solar wind, Mars was left utterly exposed. The solar wind, with its full force, slams directly into the Martian atmosphere. Over hundreds of millions of years, this relentless bombardment has been stripping the atmosphere away, molecule by molecule, in a process known as sputtering. NASA's Maven spacecraft has directly observed this atmospheric erosion in action. The solar wind transfers energy to the atoms and molecules in the upper atmosphere, giving them enough velocity to escape Mars's relatively weak gravity and fly off into space. This is why Mars today is a cold, desiccated desert. Its protective blanket was slowly and steadily torn away by an unseen, unyielding force. The solar wind, therefore, is not just a stream of particles. It is a sculptor of planetary destinies, a key factor in determining which worlds can retain the conditions necessary for life and which are destined to become barren wastelands. For over a century, Einstein's theory of general relativity gave us a whole new way to see gravity, not as a simple pull, but as the curvature of the cosmic stage of spacetime. But his equations predicted something even more astonishing, a phenomenon so subtle that Einstein himself doubted we would ever detect it: gravitational waves. Imagine the fabric of spacetime not as a static, rigid stage, but as a vast, flexible membrane like the surface of a tranquil pond. Now drop two incredibly heavy stones into that pond. The impact would send ripples spreading outward in all directions, gently bobbing any leaves or twigs floating on the surface. Gravitational waves are the cosmic equivalent of those ripples. They are literal distortions in the geometry of spacetime itself, propagating outward at the speed of light from the most cataclysmic events in the universe. The energy required to create a ripple in spacetime is almost beyond comprehension. These waves are generated by the most violent motions of mass imaginable. Picture two black holes, each with masses tens of times greater than our Sun, locked in a final, deadly orbital dance. As they spiral inward, moving at a significant fraction of the speed of light, they churn the spacetime around them. Their immense acceleration and rapid motion don't just warp the local space, they launch powerful waves that carry energy away, much like a spinning lawn sprinkler flings water outward. This loss of energy causes the black holes to spiral even closer, faster, until they finally collide and merge into a single, more massive black hole. In the final fraction of a second of this merger, an enormous burst of gravitational waves is ejected into the cosmos. The same process occurs with incredibly dense neutron stars, the collapsed cores of dead suns, spinning around each other before they crash together in an explosion that forges heavy elements like gold and platinum. These are not gentle events, they are the universe's most powerful earthquakes, sending shudders through the very fabric of reality. Detecting these ripples, however, presented a challenge of almost insane precision. A passing gravitational wave does something extraordinary. It stretches space in one direction while simultaneously compressing it in the perpendicular direction. As the wave passes through an object, it very slightly alters its shape. The problem is that the effect is vanishingly small. For even the most powerful cosmic events, the change in length a wave causes is smaller than 1/10,000th the diameter of a proton. To have any hope of measuring this, scientists built one of the most sensitive instruments ever conceived, the Laser Interferometer Gravitational Wave Observatory, or LIGO. Each LIGO observatory consists of two arms, each 4 kilometers long, arranged in an L shape. Inside these vacuum tubes, a powerful laser beam is split and sent down each arm, reflecting off perfectly suspended mirrors and recombining. Under normal conditions, the light waves cancel each other out, but when a gravitational wave passes through Earth, it minutely changes the length of one arm relative to the other, just by a fraction of the width of a proton. This tiny change disrupts the laser light's perfect cancellation, creating a flicker of light that is detected. To rule out local vibrations from trucks, earthquakes, or even falling trees, 2 identical detectors were built thousands of kilometers apart in Louisiana and Washington state. A real gravitational wave would sweep through both facilities at nearly the same instant, creating the same unique signal. In September 2015, after decades of development, this incredible effort paid off. Both LIGO detectors recorded a signal that matched exactly what supercomputer simulations predicted for the merger of 2 black holes about 1.3 billion light-years away. The signal, a rising chirp that lasted only a fraction of a second, represented the final orbits and collision of black holes 36 and 29 times the mass of our Sun. In that brief moment, the equivalent of 3 solar masses was converted directly into pure energy in the form of gravitational waves, making it the most powerful single event ever witnessed by humanity. This first direct detection opened an entirely new window on the cosmos. For the first time, we were not just seeing the universe, we were listening to it, feeling its vibrations. Gravitational waves are the universe's way of broadcasting the most violent, energetic steps in the celestial dance, allowing us to probe the nature of gravity itself in the most extreme environments imaginable, from the edge of a black hole's event horizon to the heart of a neutron star collision. While we have witnessed the colossal power of gravitational waves and the relentless stream of the solar wind, some of the most elegant unseen forces operate on a far more delicate scale, meticulously shaping the cosmic environment grain by tiny grain. This brings us to a subtle but profoundly important effect known as the Poynting-Robertson effect, a gentle yet relentless drag that governs the ultimate fate of cosmic dust. To understand it, picture a single microscopic speck of dust orbiting the Sun. Like a planet, this dust grain has a certain orbital velocity and angular momentum which keeps it on a stable path. But unlike a planet, this tiny particle is constantly bathed in the intense radiation of sunlight, and it is the interaction with this light that seals its celestial destiny. The key lies in a concept from relativity. While light has no mass, it does carry momentum. When a photon of sunlight strikes the dust grain, it is absorbed, and its momentum is transferred to the particle, giving it a tiny push in the direction the light was traveling, radially outward from the Sun. You might think this outward push would simply fling the particle away, but the situation is more nuanced because the dust grain is also moving in its orbit. From the perspective of the grain, the sunlight isn't coming from directly ahead. Due to its own orbital motion, the light appears to arrive from a slightly forward direction, a phenomenon known as aberration. So when the grain absorbs the photon, it receives a slight forward kick, as if being given a tiny boost in its orbital direction. However, the story doesn't end there. The grain heats up from absorbing this energy and then re-radiates it away as thermal radiation in all directions equally, a process called isotropic re-radiation. This is the crucial part. While the absorption was directional, giving a forward push, the re-radiation is symmetric, pushing equally in all directions. The net result of this entire cycle, the directional absorption followed by the symmetric re-radiation, is a tiny but constant loss of energy and, more importantly, a loss of angular momentum. It's as if the particle is applying a minuscule brake against its own direction of motion with every single interaction with sunlight. Over countless orbits, this braking effect accumulates. The dust grain cannot maintain its original orbital speed. It begins to slow down just enough to cause its orbit to decay. Like a satellite experiencing atmospheric drag, the particle starts a slow, inexorable spiral inward, journeying closer and closer to the star it orbits. This unseen drag force has a very visible consequence right here in our own solar system, the zodiacal light. On a very dark, clear night away from city lights, you might see a faint, diffuse glow stretching up from the horizon along the path of the ecliptic after sunset or before sunrise. This soft cone of light is not a distant galaxy or a ghostly cloud. It is sunlight scattered by countless billions of dust grains orbiting the sun in the inner solar system. This vast lens-shaped cloud of interplanetary dust is known as the zodiacal dust cloud. The Poynting-Robertson effect is the primary recycling mechanism for this dust. Comets and asteroid collisions constantly replenish the cloud with fresh debris, but the Poynting-Robertson effect acts as a cosmic conveyor belt, steadily spiraling these particles inward over timescales of thousands to hundreds of thousands of years. Without this effect, the dust would simply accumulate in its original orbits, creating a far more opaque and chaotic environment. Instead, the gentle drag ensures a continuous flow, a slow-motion rainfall of dust toward the sun that creates the beautiful, ethereal glow of the zodiacal light. The implications of this subtle force extend far beyond our local cosmic neighborhood, playing a critical role in the growth of planets and stars themselves. In the early stages of a solar system's formation, a young star is surrounded by a swirling protoplanetary disk of gas and dust. Within this disk, tiny dust grains are the building blocks of planets. As these grains orbit, they too experience the Poynting-Robertson effect. The larger grains are less affected, but the smallest particles feel the drag most strongly, causing them to spiral inward toward the central star. This inward migration serves two vital purposes. First, it helps to clear the inner regions of the disk of fine dust, allowing larger planetary embryos to form without being bombarded by a fog of tiny particles. Second, and perhaps more importantly, this inward spiraling dust delivers a steady stream of raw material directly to the growing star, contributing to its final mass. It also enriches the inner disk with material that originated from the colder outer regions, potentially delivering water ice and other volatile compounds to the zones where rocky planets like Earth are forming. In this way, the Poynting-Robertson effect is not just a destroyer of dust. It is a subtle architect, helping to orchestrate the distribution of material that will eventually coalesce into new worlds and determine the final composition of a star. It demonstrates that even the most gentle and imperceptible of forces, acting over immense spans of time, can shape the architecture of entire planetary systems. From the gentle, predictable spiral of interplanetary dust to the violent ripples of colliding black holes, we have seen how unseen forces sculpt the cosmos across vast scales of space and time. But to find the most profound and ancient force of all, we must journey back to the very beginning, to a moment before stars, before galaxies, before even atoms had formed. We must venture into the first fleeting instants after the Big Bang, where the universe was a seething, hot, and unimaginably dense soup of pure energy. And in that primordial fireball, we encounter a force so subtle it operates on the very edge of reality, a force that planted the seeds for everything we see today, the random, ghostly flicker of quantum fluctuations. At this smallest of scales, the world behaves in ways that defy common sense. According to quantum mechanics, empty space is never truly empty. Even in a perfect vacuum, there is a fundamental uncertainty, a constant, restless energy. For fleeting moments, pairs of particles and antiparticles spontaneously pop into existence, borrowing energy from the vacuum before almost instantly annihilating each other and returning it. These are quantum fluctuations, tiny, temporary bubbles of something emerging from nothing, a consequence of the Heisenberg uncertainty principle that governs the subatomic realm. In the everyday world, these fluctuations are utterly negligible, their effects vanishingly small. But in the first fraction of a second of our universe's life, something extraordinary happened that would magnify these quantum whispers into a cosmic roar. This event is known as cosmic inflation, a theory proposing that the universe underwent a period of hyper-fast, exponential expansion, inflating from a subatomic speck to something much larger than our entire observable universe in less than a billionth of a billionth of a billionth of a second. During this incredible growth spurt, those tiny quantum fluctuations, which were once smaller than a single proton, were stretched to astronomical sizes. The microscopic hills and valleys in the energy field of the infant universe were inflated to become macroscopic variations in density. Imagine taking a perfectly smooth ball of dough with only the tiniest random variations in texture at the microscopic level. Then, in an instant, you inflate that ball of dough to the size of the entire Earth. The once imperceptible texture variations would now be enormous mountains and deep valleys stretching across continents. Inflation did exactly this to the fabric of spacetime. These stretched-out density variations were not just wrinkles in empty space. They were imperfections in the distribution of matter and energy. Slightly denser regions had a tiny bit more gravitational pull than slightly less dense regions. After inflation ended and the universe continued its expansion at a more sedate pace, gravity got to work on these imperfections. Over hundreds of millions of years, the slightly denser patches acted as gravitational seeds, pulling in more and more matter from their surroundings. They grew like cosmic snowballs, accumulating gas, primarily hydrogen and helium, eventually becoming dense enough to collapse and ignite the first stars, which then gathered into the first galaxies. The great cosmic web of galaxy clusters and vast, empty voids that we observe in the universe today is not a random pattern. It is a fossilized imprint, a colossal map of those initial quantum fluctuations, blown up to the largest possible scale by inflation. This connection is one of the most breathtaking in all of science. It directly links the bizarre, probabilistic rules of the quantum world, which operate on scales a billion times smaller than an atom, to the grandest architecture of the cosmos, the distribution of galaxies across billions of light years. The majestic spiral of Andromeda, the immense Virgo cluster, and the vast emptiness of the Boötes void all owe their existence to random, microscopic tremors in the first moment of time. It suggests that the universe we inhabit is not perfectly smooth and uniform by accident, but is instead a direct consequence of the fundamental uncertainty woven into the fabric of reality. The largest structures we can possibly observe are, in their origin, the children of the smallest possible events. Einstein's theory of general relativity gave us a universe where mass tells spacetime how to curve, and curved spacetime tells mass how to move. But what happens when that mass isn't just sitting still, but is spinning? The theory predicts an even more mind-bending phenomenon, a kind of cosmic whirlpool effect where a rotating object doesn't just bend the stage of spacetime, it actively drags that stage around with it. This is frame dragging, and it's as if space and time themselves become a viscous fluid caught in the vortex of a rotating giant. A helpful way to visualize this is to think of a bowling ball spinning in a vast vat of thick honey. If the ball were stationary, it would simply create a stationary depression in the honey. But if you start to spin the ball, the sticky honey closest to its surface would be pulled along with the rotation. This would create a twisting, swirling motion in the fluid around the ball. The spinning ball is dragging the honey around with it. According to Einstein, a massive rotating body like a planet or a star does something very similar to the fabric of spacetime itself. Its rotation literally twists the local spacetime, pulling it around in the direction of the spin. It's not just the object that's moving. The very coordinate grid of space and time is being dragged along for the ride. Measuring such an incredibly subtle effect posed a monumental challenge for physicists. The distortion is minuscule for an object like Earth. To test this prediction, NASA and Stanford University developed one of the most precise experiments ever conceived, the Gravity Probe B mission. Launched in 2004, this satellite was essentially a flying gyroscope. It carried 4 ultra-spherical, perfectly polished quartz gyroscopes, spinning in a vacuum at near-perfect stillness. The idea was brilliantly simple. In a universe without frame dragging, the spin axis of these gyroscopes, once aligned with a distant guide star, should have remained fixed forever, like a cosmic compass needle pointing in one absolute direction. But if Einstein was right and the rotating Earth was dragging spacetime around it, the gyroscopic axis would be ever so slightly tugged out of alignment over time. The satellite had to account for another, larger effect called the geodetic effect, which is the warping of space due to Earth's mass alone. But after accounting for that, the mission scientists were looking for a tiny additional drift, a signal of frame dragging. After a year of collecting data and years more of painstaking analysis to eliminate sources of error, the Gravity Probe B team announced their results. They had indeed detected the frame dragging effect caused by Earth's rotation, measuring it with stunning precision and providing a direct, experimental validation of this strange consequence of general relativity. It was a triumphant confirmation that our planet's rotation doesn't just affect the air and water on its surface, but the fundamental geometry of reality around it. While the effect is tiny around Earth, its implications become truly dramatic around the most extreme objects in the universe, rapidly spinning black holes. Around a rotating or black hole, frame dragging becomes so powerful that it fundamentally alters the landscape. Just outside the event horizon, the point of no return, lies a region called the ergosphere. This is an oblate, pumpkin-shaped region where frame dragging is so intense that spacetime itself is forced to rotate faster than the speed of light. Nothing can move faster than light through space, but here, space itself is moving, carrying everything within it along in a mandatory cosmic whirlpool. Within the ergosphere, it is impossible for any object to remain stationary. No matter how powerful your rockets, you cannot fight the current of spinning spacetime. You are compelled to rotate with the black hole. This bizarre region is not a one-way street like the event horizon. Particles can enter, and if they are cleverly split, one part can fall in while the other is flung out with more energy than it entered with, in a process known as the Penrose process. This is a theoretical way to extract rotational energy from a black hole itself. The intense frame dragging in the ergosphere also has profound effects on the accretion disks of hot gas that swirl around these black holes. It can cause the inner parts of the disk to precess and wobble, and it is thought to be the engine that powers the incredibly focused jets of material that shoot out from the poles of some active black holes at nearly the speed of light. Near a spinning black hole, frame dragging transforms from a subtle curiosity into a dominant, violent force that dictates the fate of matter and energy. demonstrating that rotation imprints itself on the cosmos in ways that are both beautiful and terrifying. We have journeyed from the cosmic whirlpools of frame dragging around black holes to the quantum seeds of the universe itself, witnessing how motion and rotation are fundamental to the cosmos. But there is another incredible consequence of a spinning world, one that generates a protective shield that is absolutely vital for life as we know it. This brings us to the unseen force of the dynamo effect, the hidden engine that creates magnetic fields around planets and stars. Think of it like this: a magnetic field is an invisible force field, but it is not a permanent, static thing. It is a dynamic phenomenon, a living structure that must be continuously generated and sustained. And the power source for this incredible feat is the churning, convective motion deep within a celestial body. The basic ingredients for a cosmic dynamo are surprisingly straightforward, yet their combination creates something magical. You need three things: a large volume of an electrically conductive fluid, motion within that fluid, and rotation. Here on Earth, the conductive fluid is the molten iron and nickel in our planet's outer core, a seething ocean of metal heated to thousands of degrees. This fluid is in constant motion due to convection. Heat from the inner core rises, cools as it reaches the outer boundary, and then sinks again, creating a vast, slow-moving circulation pattern. But the crucial third ingredient is our planet's rotation. As Earth spins on its axis, this rotation organizes the chaotic convective motions, twisting them into a more orderly pattern. It's this combination, moving conductor plus rotation, that transforms a planet into a powerful electromagnetic generator. The process itself is a beautiful feedback loop. It starts with a tiny, pre-existing magnetic field, perhaps left over from the early solar system. As the conductive molten metal moves across these faint magnetic field lines, it acts like a wire moving through a magnet, which, according to the laws of electromagnetism, induces an electrical current to flow within the metal. This electrical current, in turn, generates its own magnetic field. Now, here's the clever part. If the motion of the fluid is just right, specifically, if it's twisted by the planet's rotation in a way that reinforces the original field, this newly generated magnetic field adds to the old one, making it stronger. This stronger field then induces a stronger current, which creates an even stronger magnetic field, and so on. This self-amplifying loop continues until the magnetic field reaches a strength limited by the energy available from the convective motion. It's a perfect example of a self-sustaining system, where the motion of a fluid continuously regenerates the very magnetic field that guides its own generation. This process is not unique to Earth. Jupiter's immensely powerful magnetic field is generated by the convection of metallic hydrogen deep within its interior. Even the Sun, a massive ball of plasma, operates as a giant dynamo with its magnetic field generated by the complex motions of electrically charged gas in its outer layers. The importance of this self-generating force cannot be overstated. Without the dynamo effect constantly at work in Earth's core, our global magnetic field would slowly fade away over tens of thousands of years. And without that magnetic shield, the Earth would be a very different and far more hostile world. Our magnetosphere acts as a defensive barrier, deflecting the relentless, high-energy particles of the solar wind. Without it, this constant bombardment would steadily strip away our atmosphere, much like what happened to Mars when its core cooled and its dynamo ceased. More directly, the unshielded radiation would make life on the surface incredibly difficult, if not impossible, by damaging cells and increasing mutation rates. The dynamo effect, therefore, is not just an interesting physical curiosity. It is a fundamental guardian of our biosphere, an unseen planetary process that actively maintains the conditions necessary for a thriving world. We can also see the dynamo's handiwork in the activity of our Sun. The solar dynamo, driven by the churning plasma in the Sun's convection zone, is responsible for the famous 11-year sunspot cycle. Sunspots are temporary, dark patches on the Sun's surface that mark areas of intense magnetic activity. Over the cycle, the Sun's magnetic field becomes increasingly tangled and complex, leading to a rise in sunspots, solar flares, and coronal mass ejections. Then the field reverses polarity and the cycle begins anew. This periodic ebb and flow of magnetic activity, which influences space weather throughout our solar system, is a direct manifestation of the dynamo process operating within our star. From the steady shield around our planet to the rhythmic pulse of our Sun, the dynamo effect demonstrates how internal motions, harnessed by rotation, create powerful external forces that shape the environment of entire planetary systems. It is a hidden engine whose hum is the silent, protective vibration of a living world. Moving from the powerful internal dynamos that generate magnetic fields, we encounter a force of exquisite subtlety and mathematical beauty, one that orchestrates celestial motion through a kind of gravitational conversation. This is the principle of orbital resonance, an unseen harmony where the rhythms of orbiting bodies synchronize, creating stability out of chaos and carving order into the fabric of the solar system. It all comes down to timing. An orbital resonance occurs when two bodies exert a regular, periodic gravitational influence on each other because their orbital periods form a simple whole number ratio. For example, if one moon orbits its planet exactly twice for every single orbit of another moon, they are in a 2-1 resonance. This isn't a coincidence. It's a stable configuration where their gravitational nudges reinforce each other in a consistent, repeating pattern. Think of it like pushing a child on a swing. If you push at random intervals, your efforts are inefficient and the swing's motion is erratic. But if you push at exactly the right moment in the swing's arc, at the resonant frequency, each small push adds energy constructively, building a strong, rhythmic motion with minimal effort. Orbital resonances work in a similar gravitational fashion, with small, rhythmic tugs adding up over time to create profound and lasting effects. One of the most stunning examples of this celestial harmony is found orbiting Jupiter with its three inner moons, Io, Europa, and Ganymede. These three worlds are locked in an intricate gravitational dance known as the Laplace resonance. For every single orbit Ganymede makes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise 1:2:4 ratio means the three moons periodically line up in the same configuration, with Io, the innermost and most volcanic world in the entire solar system, feeling the strongest repeated tug. As Europa and Ganymede align with Io, their combined gravitational pull stretches and squeezes Io's interior relentlessly. This constant, rhythmic flexing generates immense tidal friction, heating Io's core to the point of melting its rock. The result is a world ablaze with hundreds of active volcanoes, constantly erupting and resurfacing the moon in a torrent of sulfur and lava. Io's hellish landscape is a direct product of this resonant partnership. Without the stabilizing, periodic pulls from its siblings, the gravitational heating would be chaotic and less intense. The resonance provides a clockwork regularity to the process, turning Io into a permanent geologic inferno and demonstrating how a resonant interaction can literally shape the physical nature of a world. But resonances are not always about stabilization and heating. They can also be agents of chaos and emptiness. This destructive power is clearly visible in the main asteroid belt between Mars and Jupiter. If you were to map the orbits of all the asteroids, you would notice striking, sharp gaps where almost no asteroids are found. These are the Kirkwood gaps, and they exist at specific distances from the Sun where an asteroid's orbital period would resonate with Jupiter's. For instance, an asteroid in a 3 or 1 resonance with Jupiter would complete 3 orbits for every 1 orbit of the giant planet. This means that every time the asteroid returns to the same point in its path, Jupiter is in the same position, exerting a gravitational pull in the same direction. Instead of these pulls averaging out over time, they consistently reinforce each other, giving the asteroid's orbit a series of small but persistent kicks. Over millions of years, these repeated gravitational shoves from Jupiter accumulate, dramatically altering the asteroid's path. The orbit becomes more and more elongated or eccentric until it crosses the paths of other planets, eventually leading to a collision or being flung out of the belt entirely. The Kirkwood gaps are not regions where asteroids never formed. They are regions where resonances have efficiently cleared them out, acting as gravitational vacuum cleaners that maintain these empty lanes within the bustling traffic of the asteroid belt. The influence of these resonant harmonies extends far beyond our own solar system, helping us understand the strange configurations of distant worlds. Astronomers have discovered many exoplanet systems where planets are locked in tight orbital resonances. The TRAPPIST-1 system, for example, features 7 Earth-sized planets whose orbits are choreographed in a complex chain of resonances. This intricate gravitational ballet is likely crucial for the long-term stability of such a compact system, preventing the planets from perturbing each other into collision courses. Resonances can also explain the peculiar, highly elongated orbits of some exoplanets. A distant, massive companion world, through a mechanism like the Kozai resonance, could periodically exchange orbital eccentricity and inclination with a smaller inner planet, creating a world that swings wildly close to its star before hurtling out to the frigid depths of its system. These resonant interactions are a universal language of gravity, a subtle form of communication that allows celestial bodies to influence each other across vast distances without direct contact. They show us that the solar system is not just a collection of independent objects following lonely paths, but an interconnected web where the timing of one orbit can dictate the destiny of another, all orchestrated with the silent, mathematical precision of unseen gravitational rhythms. Now, let's turn our attention to a force so delicate that its influence was once thought to be negligible. A gentle push born not from gravity or magnetism, but from the simple, everyday act of warming in the sunlight. This is the Yarkovsky effect, a subtle thermal nudge that proves how even the faintest whisper of energy can, given enough time, rewrite the trajectories of worlds. For large planets and moons, this effect is utterly insignificant, lost in the overwhelming pull of gravity. But for small asteroids, particularly those the size of a house or a mountain, the Yarkovsky effect becomes a master pilot, a silent engine that can steer them across the solar system over millions of years. The principle is beautifully straightforward, yet its consequences are profound. An asteroid orbiting the Sun is constantly bathing in solar radiation. Its sunlit side, the day side, absorbs this energy, heating up. Like a rock warming in the afternoon sun, it eventually re-radiates that heat back into space as infrared light. The crucial detail is that this re-radiation doesn't happen instantly. There's a time lag. The asteroid continues to rotate, carrying the heat from the day side over to the night side. So, the warmest part of the asteroid is not necessarily directly facing the Sun, but is slightly offset, a phenomenon known as thermal lag. This delay is the secret to the Yarkovsky effect's power. When the asteroid re-radiates the heat from its now warm night side, that infrared light carries away momentum. Because physics demands conservation of momentum, the asteroid itself receives a tiny push in the opposite direction. It's a minute version of the recoil you feel when you spray water from a garden hose. The key is that this thermal thrust is anisotropic, meaning it's not perfectly balanced. For a prograde rotator, an asteroid spinning in the same direction it orbits the hottest point is on the late afternoon side. This means the thermal radiation pushes slightly against the direction of motion, acting like a gentle brake. This loss of energy causes the asteroid to spiral slowly inward toward the Sun. Conversely, an asteroid with a retrograde rotation, spinning backwards relative to its orbit, has its hottest point on the pre-dawn side. In this case, the thermal thrust gives it a slight forward push, adding energy and causing it to spiral outward, away from the Sun. The direction of an asteroid's spin, therefore, becomes a celestial steering wheel, dictating its long-term migration through the solar system. The true power of this effect lies in its relentless cumulative nature. The thrust from a single day of sunlight is unimaginably small, perhaps equivalent to the weight of a grape on Earth. But asteroids have time on their side. They orbit for millions, even billions of years. Day after day, year after year, this minuscule push steadily adds up. Over an eon, it can change an asteroid's velocity by hundreds of meters per second, enough to shift its orbit by distances greater than that between the Earth and the Sun. This makes the Yarkovsky effect the primary delivery mechanism for transporting asteroids from the main belt, that vast reservoir of rocky bodies between Mars and Jupiter, into the inner solar system where they become near-Earth objects. Without this thermal nudging, the gravitational influences of planets might not be enough to dislodge asteroids from their stable orbits. The Yarkovsky effect acts as a slow but persistent conveyor belt, gradually moving material from the main belt into orbital regions where Jupiter's gravity can then give them a more forceful kick, sending them on a path that might one day cross Earth's orbit. This invisible force has moved from theoretical curiosity to a critical factor in planetary defense. When astronomers try to predict the long-term path of a potentially hazardous asteroid, they can no longer rely solely on gravity. They must account for the Yarkovsky effect, which acts as a continuous, non-gravitational acceleration. A tiny miscalculation in this thermal thrust over decades can lead to a massive error in predicting an asteroid's position a century from now. A famous example is the asteroid Apophis, which initially caused concern for a potential close approach in 2029. Early gravitational models showed a small but real risk of impact. However, once astronomers were able to measure the Yarkovsky effect on Apophis by observing its subtle orbital drift over several years, they could refine its trajectory. This detailed understanding, which included the asteroid's size, shape, spin, and thermal properties, allowed them to rule out an impact for the foreseeable future. The Yarkovsky effect transformed Apophis from a threat into a subject of study, demonstrating that accurately forecasting our cosmic future depends on understanding even the most gentle of unseen forces. It forges a direct and sobering link between the simple physics of a warming rock and the long-term security of our planet. Now, let's scale up our perspective from the slow, steady nudges on asteroids to a force of cosmic violence that operates on the scale of entire galaxies. We venture into the crowded, chaotic environments of galaxy clusters, where we encounter the 15th unseen force, the brutal, stripping power of ram pressure. To grasp this concept, imagine you're riding in a car on the highway and you stick your hand out the window. You feel a powerful push against your palm, a force trying to push your hand backward. That force is ram pressure, the resistance you feel from moving through a fluid, which in this case is the air. Now, let's replace your hand with an entire galaxy, and replace the air with the superheated, thin gas that fills the vast spaces between galaxies within a cluster. This is the intergalactic medium, a plasma that can reach temperatures of tens of millions of degrees. When a galaxy, particularly a spiral galaxy rich with cold gas, falls into a dense galaxy cluster, it begins to move at tremendous speeds through this incredibly hot, thin soup. The galaxy experiences a colossal version of that same pressure you felt on your hand, and the consequences for the galaxy are catastrophic. The most vulnerable part of a spiral galaxy is its reservoir of cool gas and dust. This material, concentrated in the galaxy's disk, is the raw fuel for future star formation. It's this gas that collapses under gravity to ignite new stars. But as the galaxy plows through the cluster's intergalactic medium, the ram pressure acts like a cosmic windstorm of unimaginable force. It doesn't gently push the galaxy aside. Instead, it grips the tenuous gas within the galaxy and begins to rip it away. The process is direct and merciless. The galaxy's own gravitational pull tries to hold onto its gas, but for the gas clouds in the outer regions of the disk, the relentless ram pressure is stronger. It simply sweeps the gas out of the galaxy, leaving behind a visible trail of stripped material like cosmic exhaust fumes in the galaxy's wake. Astronomers have observed these jellyfish galaxies within clusters, with long, gaseous tails streaming behind them, clear evidence of this violent stripping in action. This loss of its gaseous fuel has a profound and irreversible effect on the galaxy's destiny. Without a continuous supply of cold gas, the galaxy can no longer form new stars. The great stellar nurseries, the bright pink emission nebulae that dot the spiral arms, slowly fade away as the last of their gas is used up or stripped out. Star formation is quenched. The galaxy's vibrant, blue, short-lived massive stars, the ones that give spiral galaxies their bright, youthful appearance, burn out and are not replaced. What remains is an aging population of longer-lived, redder stars. Over time, the galaxy's elegant spiral structure, which was defined by waves of star formation, begins to blur and fade. The galaxy transforms from a star-forming spiral, full of dynamic activity, into a quiet, featureless elliptical galaxy, a smooth, red and orange collection of old stars, a celestial retirement home. This metamorphosis isn't driven by internal processes. It's an external attack, a dramatic example of how a galaxy's environment dictates its evolution. A spiral galaxy isolated in a quiet region of space could continue forming stars for billions of years, but one that falls into a bustling cluster can have its lifeblood drained away in a relatively short cosmic timescale, its future stolen by the invisible, relentless push of the medium through which it moves. Our exploration of celestial forces has revealed how resonances can create stability and how subtle thermal effects can steer asteroids. But now we encounter a gravitational interaction of such elegant complexity that it resembles a cosmic dance where partners periodically exchange their most defining characteristics. This is the Kozai mechanism, a fascinating process that occurs within a special kind of family, a triple system. Imagine a close-knit binary pair, perhaps two stars orbiting each other in a tight, circular embrace. Now introduce a third, more distant body, a stellar companion that orbits the pair on a wider, inclined path. In this three-body arrangement, a remarkable gravitational conversation begins. The gravitational tug from the distant perturber doesn't just pull on the binary. It interacts with the system in a way that creates a rhythmic, cyclical exchange. The Kozai mechanism describes how, over long periods, the inner binary's orbit can trade its circular shape for a highly elongated, eccentric one, while simultaneously the angle of its orbit, its inclination changes. It's as if one orbit can become more stretched out while the other becomes more tilted. And then, after thousands of years, they swap back again in a continuous, periodic cycle. The underlying physics involves a conservation law related to the system's orientation in space. In a simplified, isolated two-body system, both the eccentricity and the inclination of an orbit remain constant. But when a third body on an inclined orbit is added, it breaks the symmetry. The gravitational influence of the perturber causes the inner binary's orbit to precess, meaning the long axis of its elliptical path slowly rotates. However, a specific component of the system's angular momentum, perpendicular to the orbital plane of the outer body, must be conserved. This constraint forces a trade-off. If the inner orbit becomes more face-on relative to the distant perturber, decreasing its inclination, it must compensate by becoming more circular. Conversely, if it becomes more edge-on, increasing its inclination, it is forced to become more eccentric to satisfy the conservation law. This leads to the signature oscillation. The eccentricity of the inner binary rises as its inclination decreases, reaches a maximum when the inclination is lowest, and then the process reverses. The two parameters are locked in a gravitational seesaw, perpetually exchanging their values. This mechanism provides a compelling explanation for some of the most puzzling orbits we observe in our galaxy, particularly the wildly eccentric paths of certain exoplanets. Astronomers have discovered gas giant planets in other solar systems that follow orbits which are not the near-perfect circles we see in our own. Instead, these hot Jupiters swing incredibly close to their host star before hurtling out to the frigid depths of their system on long, looping trajectories. How did they get there? It's unlikely they formed so close to their star's intense heat. A leading theory is the Kozai mechanism. In this scenario, the exoplanet initially formed in a circular orbit much farther out. But it had a distant stellar companion, another star orbiting the pair. Over billions of years, the Kozai oscillations periodically pumped up the planet's orbital eccentricity. During a phase of maximum eccentricity, the planet would pass perilously close to its star at Periastron, the closest point in its orbit. At this point, tidal forces from the star could act as a brake, circularizing the orbit at this much smaller distance. The result is a gas giant now parked in a tight, circular orbit close to the star, a silent relic of a dramatic gravitational history orchestrated by an unseen stellar partner. The influence of this mechanism extends to the most extreme gravitational environment we know of, the heart of our own Milky Way galaxy. There, orbiting the supermassive black hole known as Sagittarius, a star, is a population of stars on incredibly fast, often highly eccentric orbits. These stars, known as the S-stars, are a subject of intense study. Their peculiar paths are difficult to explain if they formed in placid isolation. The Kozai mechanism offers an elegant solution. Many of these stars might originally have been part of binary star systems that wandered too close to the black hole. The immense gravity of the black hole could have torn the binary apart, capturing one star while flinging the other away. But before that violent divorce, the binary system, under the influence of the black hole as the ultimate distant perturber, could have experienced Kozai oscillations. This would have excited the eccentricities of the star's orbits, setting them on the wild, elliptical paths we observe today. The rhythmic dance of the Kozai mechanism, therefore, adds a layer of sophisticated complexity to the chaotic ballet around our galactic center, demonstrating that even in the realm of a supermassive black hole, the subtle gravitational interplay of three bodies can leave a distinct and lasting signature on the motion of stars. We have explored forces that sculpt galaxies and steer asteroids, but now we must confront perhaps the most counterintuitive idea of all, that the very emptiness of space itself holds a mysterious, latent power. This brings us to the enigmatic realm of vacuum energy, a concept that pushes our understanding of physics to its very limits. The very name sounds like a contradiction. How can a vacuum, the very definition of nothingness, contain energy? To grasp this, we have to venture into the bizarre world of quantum mechanics, where the rules of common sense no longer apply. In our everyday experience, empty space is just that, empty. A perfect vacuum is a volume from which every single atom of matter has been removed. But according to quantum field theory, which describes the behavior of particles and forces at the most fundamental level, this classical idea of emptiness is an illusion. What we perceive as a void is in fact a seething, bubbling cauldron of activity. This activity is driven by the Heisenberg uncertainty principle, which states that on the tiniest scales, there is a fundamental limit to how precisely we can know certain properties like energy and time. One consequence of this principle is that energy can be borrowed from nowhere, so long as it is paid back within an incredibly brief window of time. This allows for the spontaneous and continuous creation of pairs of virtual particles, a particle and its antiparticle, that flicker into existence for a fleeting moment before annihilating each other and vanishing back into the void. This isn't just a theoretical idea, we have experimental proof of its reality. The Casimir effect demonstrates this beautifully. If you place two perfectly smooth, uncharged metal plates extremely close together in a vacuum, they will experience a faint but measurable force pushing them together. Why? Because the space between the plates is so narrow that it restricts the kinds of virtual particles that can pop into existence there. The space outside the plates, however, has no such restriction. The greater pressure from the more active virtual particle C on the outside pushes the plates together. This proves that even in a perfect vacuum, there is a background energy, a restless sea of quantum fluctuations that defies the very notion of true emptiness. This ceaseless activity of the quantum vacuum should, in theory, imbue every cubic centimeter of space with a certain energy density. This is vacuum energy. And according to Einstein's famous equation, E equals mc squared, energy has gravitational consequences. This is where the story takes a dramatic and puzzling turn, connecting the infinitesimally small quantum world to the grandest cosmic scale. When Einstein was developing his theory of general relativity, he introduced a fudge factor into his equations called the cosmological constant. His goal was to describe a static universe, one that was neither expanding nor contracting. He later called this his greatest blunder after Edwin Hubble discovered the universe was in fact expanding. But the idea of a cosmological constant never truly went away. Modern cosmology has resurrected it in a stunning new form. The accelerating expansion of the universe, driven by the mysterious dark energy, behaves mathematically exactly like a cosmological constant. And the most natural candidate for the source of this constant is the energy of the vacuum itself. In this view, vacuum energy is not just a curious quantum effect. It is a repulsive pressure inherent to the fabric of spacetime, a force that causes the universe to expand at an ever-increasing rate. But here we encounter the most profound problem in all of theoretical physics. When physicists attempt to calculate the theoretical value of the vacuum energy based on quantum field theory, the number they get is astronomically, impossibly large. It should be around 120 orders of magnitude stronger than the value we actually observe from the acceleration of the cosmos. To put that incomprehensible number in perspective, it's the difference between the energy contained in a single proton and the energy contained in the entire observable universe. This staggering discrepancy is known as the cosmological constant problem, and it represents a glaring chasm in our understanding, a clear signal that a crucial piece of the puzzle is missing. It suggests that either our theories of the quantum world are incomplete in some fundamental way when applied to gravity, or that some unknown cancelling mechanism is at work, fine-tuning the vacuum energy to the incredibly small but non-zero value we observe. The implications of this vacuum pressure are nothing short of cosmic. If dark energy is indeed the manifestation of this vacuum energy, and it remains constant, as the cosmological constant suggests, then the fate of the universe is a cold, lonely, and ever-accelerating expansion. Galaxies beyond our local group will eventually be pushed away so fast that their light will never be able to reach us. The universe will become a vast, dark, and empty expanse, with islands of galaxies forever isolated from one another. This force, born from the quantum flickering of nothingness, appears to hold the key to the ultimate destiny of everything. It forges a direct and humbling link between the frantic, uncertain dance of virtual particles on the smallest possible scale and the relentless, accelerating flight of the galaxies on the largest. The emptiness of space is not passive. It is dynamically active, and its hidden energy may be writing the final chapter of the cosmic story. But what if gravity could do more than just pull on matter or ripple the fabric of space-time? What if it could actually manipulate the very paths that light itself must follow? This brings us to one of the most visually stunning and scientifically powerful predictions of Einstein's theory: gravitational lensing, a phenomenon where gravity acts as a cosmic lens, bending and warping the light from distant objects in ways that can create mirages, magnify the faint, and map the invisible. At its heart, the principle is a direct consequence of the warping of spacetime. Remember that massive objects like stars, galaxies, and black holes create depressions in the cosmic fabric. Now imagine a ray of light traveling across this curved landscape. According to general relativity, light always follows the shortest path through spacetime, which is called a geodesic. But when spacetime is curved, the shortest path is no longer a straight line. It's a curve. So, as light passes near a massive object, its path is bent, much like a marble would curve as it rolls past the depression made by a bowling ball on that rubber sheet. The more massive the object, and the closer the light passes to it, the more pronounced the bending becomes. This isn't a tiny effect. During a solar eclipse in 1919, Arthur Eddington famously confirmed Einstein's prediction by observing that the apparent positions of stars near the sun's edge were shifted because their light was bent by the sun's gravity. It was a monumental victory for general relativity, proving that gravity could indeed reach out and steer the course of light itself. When the alignment between a distant light source, a massive foreground object, and our telescope is just right, this bending of light transforms from a simple shift into something truly magical. The foreground object, often a massive galaxy or a cluster of galaxies, acts as a gravitational lens. Instead of seeing a single, clear image of the background object, we see multiple, distorted, and magnified images. The simplest form is called an Einstein ring, where the background object, the lens, and Earth are in perfect alignment. The light from the distant source is bent in all directions around the lens, creating a perfect, or nearly perfect, ring of light around the foreground galaxy. It's a complete circle of warped reality, a cosmic halo forged by gravity. More commonly, the alignment isn't perfect, and we see multiple, stretched, and arc-like images of the same background galaxy, arranged around the lensing cluster like pieces of a shattered mirror. These are gravitational arcs, and some of the most breathtaking images from the Hubble Space Telescope showcase these immense, smeared streaks of light, which are actually entire galaxies billions of light years away. their shapes grotesquely twisted by the immense gravitational field of a closer cluster. In some intricate lenses, you can even see the same distant supernova appear multiple times in the sky, as its light takes different paths around the lens, arriving at our telescopes at slightly different times. Gravitational lensing turns the universe into a vast funhouse of mirrors, where the rules of perspective are rewritten by gravity. Beyond the sheer wonder of these cosmic mirages, gravitational lensing provides astronomers with one of their most powerful tools for exploring the universe. It functions as a natural telescope, and one with a capability we could never build ourselves. The lensing effect doesn't just bend light, it also magnifies it. The gravitational field of a massive galaxy cluster can act like a giant magnifying glass, amplifying the light of incredibly faint, distant galaxies that would otherwise be far beyond the reach of any observatory. This allows us to peer back to the very earliest epochs of galaxy formation, studying infant galaxies as they were just a few 100 million years after the Big Bang. By analyzing these magnified images, we can learn about the formation of the first stars, the growth of black holes, and the chemical composition of the primordial universe. The lens does the hard work for us, gathering and focusing light from the cosmic dawn and delivering it to our instruments. This natural telescope has opened a window to a universe we could never have seen otherwise, revealing the childhood of galaxies in stunning detail. Perhaps the most profound application of gravitational lensing, however, is its ability to make the invisible visible. We've discussed the ghostly presence of dark matter, which emits no light and cannot be seen directly. But dark matter has mass, and therefore it exerts a gravitational pull. This means it warps spacetime and contributes to gravitational lensing. When astronomers study a massive galaxy cluster, they can map the total gravitational field by carefully measuring the distortions of the thousands of background galaxies seen behind it. They can create a map of where the gravity is strongest, pinpointing the mass distribution within the cluster. When they then subtract the mass they can see the mass in the form of stars and hot gas. They are often left with a huge discrepancy. The gravitational lensing map reveals far more mass than is visible. The only explanation is that the majority of the mass is in the form of dark matter. The distorted shapes of the background galaxies are literally tracing out the invisible dark matter halo of the foreground cluster. In this way, light itself becomes a probe for the dark universe. By analyzing the subtle patterns of distortion, a technique called weak gravitational lensing, astronomers can create vast maps of the dark matter distribution across the cosmos, revealing the cosmic web of filaments and voids that dark matter weaves. Gravitational lensing, therefore, is far more than a curious optical illusion. It is a fundamental technique that uses light as a tracer, allowing us to see the gravitational footprint of the universe's dominant but hidden component, turning the bending of starlight into a precise scale for weighing the invisible. Now we venture into one of the most extreme environments the universe can create, a place where the pull of gravity is so overwhelming that it forges a cosmic engine of unimaginable power. This is the realm of accretion disks, the brilliant, swirling maelstroms of matter that form around the most compact objects in existence, black holes and neutron stars. The story begins with gravity's relentless pull. When a star ends its life, or when a wandering star ventures too close to a supermassive black hole at the center of a galaxy, it can be torn apart. The resulting debris doesn't fall straight in. Instead, because it possesses some angular momentum, it begins to orbit the central object, much like water swirling around a drain. This material settles into a flattened, pancake-like structure, the accretion disk. Friction is the key that unlocks the engine. The gas in the disk isn't a solid body. different parts orbit at different speeds, with material closer to the center moving much faster than material farther out. This differential rotation causes the gas to rub against itself, creating intense internal friction. This frictional force does two critical things. It heats the gas to incredible temperatures, turning it into a seething plasma, and it causes the gas to slowly lose orbital energy, allowing it to spiral inward, step by step, toward the central object's event horizon or solid surface. As this plasma spirals inward, it is compressed and heated to temperatures that can reach millions, even billions of degrees. At these extremes, the disk doesn't just glow with visible light. It radiates prodigious amounts of energy across the entire electromagnetic spectrum, with a peak often in the high-energy X-ray region. It is here that we encounter our 19th unseen force, radiation drag. The disk becomes so brilliantly luminous that the torrent of photons it produces, the very radiation being released by the friction, creates a formidable outward pressure. This is the same radiation pressure we discussed earlier, but operating on a truly violent scale. For the matter trying to spiral inward, this intense radiation field acts like a powerful headwind, a constant barrage of photons pushing back against the flow. This creates a fundamental tug of war at the heart of the accretion process. On one side, you have the immense gravitational pull of the black hole or neutron star, relentlessly dragging matter inward. On the other side, you have the radiation pressure from the disk itself, pushing outward with tremendous force. This delicate balance between the inward pull of gravity and the outward push of radiation determines the accretion rate, how quickly the cosmic engine can feed. When the balance is just right, the system can achieve a stable, high-energy output. But if the inflow of fresh material increases too much, the disk can become overloaded. The increased friction heats the disk even more, which in turn increases the radiation pressure. If this radiation pressure becomes strong enough, it can actually halt the inward flow of material entirely, or even blow the outer layers of the disk away in a powerful radiative wind. It's as if the engine starts to choke on its own fuel, its power output creating a feedback mechanism that regulates its own consumption. This self-regulating property is crucial for understanding why we don't see even more luminous objects in the sky. There is a theoretical maximum brightness for an accretion disk, known as the Eddington limit, beyond which radiation pressure will overcome gravity and blow the disk apart. This unseen force of radiation drag, therefore, acts as a cosmic governor, preventing these engines from consuming matter too quickly and destroying themselves in the process. The consequences of this turbulent dance are written across the high-energy sky. For a stellar mass black hole or neutron star, the accretion disk is the powerhouse behind bright X-ray binaries. As material from a companion star is siphoned off and forms a disk, the incredible heating makes these systems shine brilliantly in X-rays, flickering and varying as the complex dynamics of the disk play out. For supermassive black holes at the centers of galaxies, the accretion process is what creates quasars and other active galactic nuclei, the most persistently luminous objects in the universe. The energy output from a single quasar can outshine an entire galaxy of hundreds of billions of stars, all powered by the gravitational energy released as gas spirals into the black hole, a process masterfully regulated by the countervailing push of its own radiation. In the most dramatic cases, the interplay between gravity and radiation, channeled by powerful magnetic fields, can also launch colossal jets of material that shoot out from the poles of the system at nearly the speed of light, extending for thousands of light years. The humble force of drag, born from the light of a hot plasma, becomes the key to understanding how the universe's most formidable engines convert gravity into light, governing their growth and shaping their incredible power. We have witnessed the incredible violence of accretion disks and the subtle nudges of radiation drag, but now we turn to a force that acts as a cosmic gatekeeper, a strict boundary written not in stone but in the fundamental laws of quantum mechanics. This is the Chandrasekhar limit, a critical threshold that dictates the ultimate fate of sun-like stars and unleashes one of the most important explosions in the universe. To understand its power, we must first follow the life cycle of a typical star. A star like our Sun spends billions of years in a stable balance, with the outward pressure from nuclear fusion in its core perfectly counteracting the inward crush of its own gravity. But this balance is temporary. Eventually, the star exhausts the hydrogen fuel in its core. Without the energy from fusion to support it, the core begins to collapse under gravity's relentless pull. This collapse, however, heats the core even more, triggering a new round of fusion in a shell around it. This new fusion is so intense that it pushes the star's outer layers outward, causing it to swell into a red giant. What remains after this tumultuous phase is the star's exposed core, a fantastically dense, Earth-sized object known as a white dwarf. This stellar ember is incredibly hot, but it is no longer performing fusion. It has run out of nuclear fuel, so what force could possibly prevent this incredibly dense ball of matter from collapsing further under its own immense gravity? The answer lies in a bizarre quantum mechanical effect known as electron degeneracy pressure. Inside a white dwarf, the matter is in an extraordinary state. The gravity is so strong that all the atoms are smashed together, their electron shells completely overlapping. The atomic nuclei are packed into a crystalline lattice, while the electrons form a seething, dense quantum gas. At these incredible densities, the rules of quantum mechanics take over. One of these rules is the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. You can think of it as a cosmic rule against overcrowding in the subatomic realm. As gravity tries to compress the white dwarf even further, it tries to force these electrons into the same energy states. But the Pauli principle forbids this. The electrons resist this compression with a tremendous pressure, a force that has nothing to do with heat or motion, but arises purely from this quantum mechanical law. This is electron degeneracy pressure, an unseen force born from the fundamental aversion electrons have to being squeezed into the same space. For a long time, this pressure was thought to be strong enough to support a white dwarf of any mass, granting it eternal stability. But a young physicist named Subramanian Chandrasekhar discovered this was not the case. During a sea voyage from India to England in 1930, the 19-year-old Chandrasekhar began performing calculations that would revolutionize astrophysics. He realized that as the mass of a white dwarf increases, the gravitational squeeze becomes more intense, forcing the electron gas to higher and higher energies. According to Einstein's theory of relativity, as particles are accelerated to speeds approaching the speed of light, their mass effectively increases. Chandrasekhar found that there is a point where the electrons are pushed so close together that they are forced to move at relativistic speeds, and at this point, the electron degeneracy pressure can no longer keep up with the gravitational force. He calculated the precise maximum mass where this balance tips, a value approximately 1.4 times the mass of our Sun. This is the Chandrasekhar limit. It is not a suggestion, it is a fundamental physical boundary. Any white dwarf that remains below this mass will cool slowly over trillions of years into a black diamond in the darkness. But any white dwarf that dares to cross this line is doomed. There are two primary paths to this catastrophic crossing. The first is through a stellar partnership. If a white dwarf is in a binary system with a companion star, it can act as a cosmic vampire, using its strong gravity to siphon gas, primarily hydrogen, from its neighbor. This stolen material accumulates on the white dwarf's surface, building up layer by layer. For a time, this hydrogen may ignite in a series of smaller, superficial explosions called nova, which blast some of the material away. But if the accretion rate is just right, the white dwarf can steadily gain mass. As it inches closer and closer to the Chandrasekhar limit, the pressure and temperature in its carbon and oxygen core rise to astronomical levels. The second path is through the merger of two white dwarfs in a binary system that lose orbital energy through gravitational waves and spiral into each other. When the combined mass of the merger exceeds the limit, the result is the same. Once that critical threshold of 1.4 solar masses is crossed, the star's fate is sealed in a matter of seconds. The electron degeneracy pressure, which had been the star's sole support, catastrophically fails. With its quantum support gone, there is nothing left to fight gravity. The core collapses at nearly a quarter the speed of light. This sudden, violent compression heats the core to temperatures exceeding billions of degrees, triggering runaway nuclear fusion in an instant. Unlike the controlled fusion in a main sequence star, this is a thermonuclear inferno that rips through the entire white dwarf in a few seconds. The energy released is so immense that it completely unbinds the star, tearing it apart in a titanic explosion known as a Type Ia supernova. The blast is so incredibly bright and uniform that it can, for a brief time, outshine an entire galaxy of 100 billion stars. This remarkable consistency in their peak brightness makes Type Ia supernova one of the most important tools in cosmology, acting as the standard candles that revealed the accelerating expansion of the universe and the existence of dark energy. But the importance of the Chandrasekhar limit extends far beyond its role as a cosmic measuring stick. This single, precise number is a fundamental recycling mechanism for the cosmos. In the fiery heart of the supernova explosion, elements are forged in an intense blast of nuclear fusion. The carbon and oxygen that made up the white dwarf are fused into heavier elements like silicon, sulfur, and crucially, iron. The explosion then scatters these newly created elements far and wide, seeding the surrounding interstellar medium with the raw materials for new generations of stars, planets, and life itself. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all created in the death throes of stars that lived and died before our sun was born. The Chandrasekhar limit is the trigger for this cosmic recycling program. It is the ultimate arbiter of stellar destiny, a quantum boundary that separates a quiet, cold fade from a brilliant, universe-shaping explosion that enriches the cosmos with the very elements that make life possible. From the quantum boundary that triggers stellar explosions, we now turn to a more subtle but equally vital force, one that acts as a messenger, carrying energy across the vast and seemingly empty expanses of space. We've seen how magnetic fields create invisible structures, but how does the energy stored within those fields actually travel? The answer lies in a special kind of wave, an oscillation that can only exist in the presence of a magnetic field and a plasma. This is the Alfvén wave, a fundamental ripple in the cosmic fabric that acts as an unseen conveyor belt for energy throughout the universe. To understand it, we first need to picture a plasma, which is often called the fourth state of matter. It's a superheated gas so energetic that electrons are ripped away from their atomic nuclei, creating a soup of charged particles, ions, and electrons that can conduct electricity. And when you have a plasma and a magnetic field together, they become inextricably linked. The particles are tied to the magnetic field lines, spiraling along them like beads on an invisible wire. An Alfvén wave is a disturbance that travels along these taut magnetic field lines. Imagine plucking a guitar string. The string vibrates, and that vibration travels as a wave along its length. An Alfvén wave is a magnetic analog, a ripple that causes the plasma and the magnetic field itself to oscillate together in a coordinated motion. The wave propagates by transferring energy between the magnetic field's tension and the inertia of the plasma, creating a low-frequency wave that can travel enormous distances with very little loss of energy. It's a true wave of magnetism, a coordinated shudder that runs through the very backbone of a magnetic field. The importance of these waves becomes brilliantly clear when we look at one of the longest-standing mysteries in solar science, the coronal heating problem. The surface of the Sun, the photosphere, has a temperature of about 5,500 degrees Celsius. But when we look at the Sun's outer atmosphere, the corona, which extends millions of kilometers into space, the temperature soars to more than 1,000,000 degrees. This is completely counterintuitive. You wouldn't expect the atmosphere of a star to be hundreds of times hotter than its surface, any more than you'd expect the air around a fire to be hotter than the flames themselves. For decades, astronomers searched for the invisible heater, the leading candidate, Alfvén waves. The Sun's surface is a bubbling, convective cauldron that constantly churns its magnetic field. This churning is like someone constantly plucking the magnetic field lines that are anchored in the solar surface. These plucks generate Alfvén waves that then race upward along the field lines, carrying kinetic energy from the turbulent surface into the tenuous corona. As these waves travel upward into regions of lower density, their energy becomes more concentrated. Eventually, this wave energy is dissipated, much like an ocean wave crashing on a shore, and that energy is converted into heat through complex processes involving magnetic reconnection and wave turbulence. It's this relentless rain of Alfvén waves, generated by the Sun's constant magnetic turmoil, that acts as a continuous energy delivery service, pumping heat into the corona and solving the mystery of why the Sun's atmosphere is so inexplicably hot. But the journey of an Alfvén wave doesn't end at the corona. These magnetic ripples are also the primary engine that accelerates the solar wind. The solar wind starts off as a relatively slow flow of plasma from the Sun's corona, but it needs a boost to reach the supersonic speeds we observe throughout the solar system. Alfvén waves provide that boost. As these waves stream outward from the Sun, they transfer their momentum to the charged particles in the solar wind, pushing them along like a surfer catching a wave. This process, known as wave heating, continues to energize the wind far from the Sun, helping it overcome the Sun's gravitational pull and explaining why the wind has such high velocity. This creates a direct, invisible connection between the magnetic activity on the Sun's surface and the conditions experienced by planets billions of kilometers away. The strength and variability of the Alfvén waves leaving the Sun directly influence the speed and density of the solar wind that fills our heliosphere. When the Sun is more active with more sunspots and magnetic complexity, it generates more Alfvén waves, leading to a faster, more turbulent solar wind that can create intense geomagnetic storms when it reaches Earth. When the Sun is quiet, the Alfvén wave activity diminishes and the solar wind becomes calmer. This means that these unseen magnetic oscillations are not just a local phenomenon. They are a fundamental part of the Sun's weather system, governing the space environment for every planet, comet, and asteroid orbiting our star. The influence of Alfvén waves extends far beyond our own solar system. playing a crucial role in the dynamics of galaxies and even in the birth of stars themselves. Within our own galaxy, vast clouds of molecular gas and dust are threaded by magnetic fields. Alfvén waves are thought to travel through these clouds, helping to support them against gravitational collapse by providing a form of wave pressure. They can also transport energy and angular momentum, influencing how these clouds rotate and fragment as they begin the process of forming new stars. On a truly cosmic scale, the jets of material that shoot out from the poles of young stars or from the accretion disks of supermassive black holes are likely channeled and focused by powerful magnetic fields. Within these narrow, high-velocity jets, Alfvén waves are probably responsible for accelerating particles to incredibly high energies and for helping to stabilize the jet over immense distances. In every plasma-rich environment across the universe, from the heart of a star-forming nebula to the relativistic jets of a quasar, Alfvén waves serve as the universal mechanism for transmitting energy and organizing motion. They are the silent vibrations that orchestrate the flow of power through magnetized space, a fundamental rhythm in the symphony of cosmic forces that connects the smallest flicker of magnetic activity to the largest structures in the cosmos. Across the cosmos, vast clouds of gas and dust drift through the emptiness of interstellar space, appearing as serene, dark nebulae silhouetted against the glow of distant stars. They seem like peaceful, almost permanent features of the galaxy. But this tranquility is a cosmic illusion, a temporary state in a universe constantly pulled between creation and dissolution. The fate of these clouds, whether they will slowly dissipate or ignite into brilliant new suns, is decided by a delicate and unseen tug of war between two fundamental forces. On one side, you have the internal pressure of the gas, the relentless, microscopic motion of its molecules and atoms that pushes outward, trying to make the cloud expand. On the other side, you have the cloud's own gravity, the collective pull of every atom on every other atom, trying to make the cloud contract. For most of a cloud's life, these two forces are in a near-perfect stalemate. The gas pressure provides enough support to hold gravity at bay, maintaining the cloud in a state of equilibrium. But this balance is precarious. If the scale tips even slightly in gravity's favor, the entire cloud becomes unstable, and a chain reaction begins that will ultimately lead to the birth of stars. The invisible trigger for this cosmic transformation is a fundamental physical principle known as the Jeans instability, named after the British physicist Sir James Jeans, who first described it mathematically. The Jeans instability provides a beautifully simple but powerful criterion for predicting when a gas cloud will collapse. It all comes down to a critical threshold, a point of no return defined by two key properties of the cloud, its density and its temperature. Think of it like this: the internal pressure that supports the cloud is directly related to its temperature. A hotter cloud has faster-moving gas particles, which generate more outward pressure to resist gravity's squeeze. Conversely, a colder cloud has less internal support. The gravitational pull, however, is determined by the cloud's density, how much mass is packed into a given volume. A denser cloud has more mass in a smaller space, meaning its self-gravity is much stronger. The Jeans instability tells us that a cloud will collapse when gravity wins, which happens when the cloud is both sufficiently dense and sufficiently cold. Physicists combine these factors into a single critical value known as the Jeans mass. If the actual mass of a gas cloud is greater than its Jeans mass, collapse is inevitable. Alternatively, you can think of a Jeans length, which is the minimum diameter a cloud of a given density and temperature must have to be unstable. If a disturbance, perhaps the shock wave from a nearby supernova, compresses a region of the cloud to a size larger than this critical length, that region is destined to collapse. This elegant formula is the secret rule that governs star formation throughout the universe, a simple mathematical gatekeeper standing between a quiescent cloud and a stellar nursery. The process of collapse, once initiated, is a dramatic runaway event. Imagine a small, random fluctuation within the cloud, a slightly denser knot of gas. This knot has a slightly stronger gravitational pull than its surroundings, so it begins to attract more material, growing even denser. As it contracts, the pressure inside the knot increases, but crucially, the gravitational force increases even faster because it depends on the square of the density. The collapse therefore accelerates. However, the gas cannot simply fall inward unimpeded. As it collapses, it also heats up, much like the air in a bicycle pump gets warm when you compress it. This heating increases the internal pressure, which for a while can slow the collapse, but for a cloud that has surpassed the gene's limit, this is only a temporary delay. The key is that the gas can radiate away this heat, particularly through molecules like carbon monoxide that act as a cosmic coolant. As the heat energy escapes in the form of infrared radiation, the pressure support drops again, allowing gravity to resume its relentless work. This cycle of collapse, heating, and cooling allows the cloud to condense further and further, breaking up into smaller, denser fragments that will each go on to form individual stars or stellar systems. What began as a gentle imbalance becomes a violent, chaotic, and transformative storm of infalling gas. We can see this principle at work in some of the most iconic and beautiful structures in our galaxy, like the pillars of creation in the Eagle Nebula. These towering columns of gas and dust are not just static sculptures, they are active sites of star formation, and the gene's instability is the sculptor. The intense ultraviolet radiation from nearby massive stars is eroding the pillars, but it is also compressing them. This external pressure effectively increases the density of the gas within the pillars, pushing it over the gene's mass threshold and triggering the collapse of dense globules buried within the structures. In this way, the very forces that are destroying the pillars are simultaneously creating the conditions for a new generation of stars to be born inside them. It's a perfect illustration of the cyclical nature of the cosmos, where death gives rise to life on an astronomical scale. The gene's instability is the fundamental mechanism that allows this cycle to turn, transforming the raw material of dead stars into the fuel for new ones, ensuring that the galactic dance of light and gravity continues for eons to come. Now, let's consider a force that acts like a form of cosmic friction, a gradual but relentless braking effect that governs the motion of the largest structures in the universe. This is dynamical friction, and while it has a technical name, its principle can be grasped through a simple earthly analogy. Imagine a giant boat moving through a harbor filled with countless small buoys. As the boat's hull pushes through the water, it creates a wake behind it, a region of churned-up water that trails the vessel. Now, if those buoys were not anchored but free-floating, the boat's passage would pull them slightly into its wake through its gravitational influence. These buoys, now concentrated behind the boat, would exert their own collective gravitational pull back on it, creating a subtle drag that acts to slow the boat down. This is the essence of dynamical friction. It's not friction in the traditional sense of two surfaces rubbing together. It's a gravitational drag force that arises when a massive object, like a star cluster or an entire galaxy, moves through a cloud of lighter, less massive objects, such as individual stars or dark matter particles. The mechanism is a brilliant demonstration of gravity's far-reaching influence. As the massive object travels through its environment, its gravity perturbs the paths of the countless smaller bodies around it. It doesn't need to collide with them directly. Its gravitational field alone is enough to attract them, giving them a slight gravitational tug as it passes. These deflected particles tend to gather slightly behind the massive object, forming a gravitational wake, a region of enhanced density. It is this wake, this overdensity of matter trailing behind the moving giant, that then exerts its own gravitational pull back on the object. This pull is not symmetrical, it's strongest from behind, acting directly against the direction of motion. The net effect is a continuous, gentle braking force that steadily saps the object's momentum and energy. The more massive the object and the denser the environment it's moving through, the stronger this drag force becomes. It's a slow motion process, but over the immense timescales of the cosmos, its consequences are profound and irreversible. We see the dramatic effects of this gravitational brake most clearly in the interactions between galaxies. Our own Milky Way is not alone. It is orbited by dozens of smaller satellite galaxies, like the Large and Small Magellanic Clouds. In a universe without dynamical friction, these satellites would continue to orbit our galaxy forever in stable, elliptical paths, held in a perpetual gravitational dance. But the halo of the Milky Way is not empty. It is filled with a vast, diffuse sea of stars, globular clusters, and most importantly, an immense sphere of dark matter. As a satellite galaxy like the Sagittarius Dwarf elliptical galaxy orbits through this halo, it experiences dynamical friction. Each orbit, it plows through this unseen sea, and with every pass, the gravitational wake it creates pulls on it just a little bit more, slowing it down, robbing it of orbital energy. This energy loss causes the satellite's orbit to decay. It spirals inward slowly and inexorably, on a doomed trajectory toward the galactic center. This process of dynamical friction is the primary driver of what astronomers poetically call galactic cannibalism, where a large galaxy grows over time by consuming and merging with its smaller galactic neighbors. The ultimate fate of these satellite galaxies is a spectacular, slow-motion collision. As a dwarf galaxy spirals all the way into the core of its giant host, the tidal forces become overwhelming, stretching and tearing the smaller galaxy apart. Its stars are stripped away and added to the halo of the larger galaxy, while its gas can funnel inward, potentially triggering a burst of new star formation in the galactic center. The remnants of these ancient mergers are still visible in our own galaxy. Astronomers have identified stellar streams, long, arching rivers of stars that wrap around the Milky Way, which are the ghostly remains of dwarf galaxies that were torn apart by dynamical friction and tidal forces billions of years ago. These celestial fossils are a direct testament to this slow, grinding process of galactic evolution. On an even grander scale, dynamical friction plays a crucial role in the mergers of large, equal-sized galaxies. When two spiral galaxies of similar mass collide, dynamical friction between their overlapping dark matter, halos, and stellar populations acts as a cosmic brake, slowing their relative motion and ensuring they don't just pass through each other, but instead merge to form a new, larger elliptical galaxy. This unseen gravitational drag is therefore a fundamental architect of the universe's large-scale structure, responsible for building the giant elliptical galaxies we see at the hearts of dense galaxy clusters, and for shaping the hierarchical growth of all cosmic structures over billions of years. Now, let's explore a force that turns the very nature of gravity on its head, transforming it from an obstacle into an accomplice for space travel. This is the Oberth effect, a brilliant and counterintuitive trick of orbital mechanics that allows a spacecraft to extract the maximum possible punch from its rocket fuel. The principle sounds almost like a loophole in physics, a rocket engine burning its fuel while the spacecraft is moving at high speed produces a greater change in velocity than the same burn at low speed. It's not about the engine working harder. It's about the fuel itself carrying more usable energy when it's expelled at a moment of peak velocity. To understand why, we need to think about energy in two forms. A rocket and its propellant possess kinetic energy, which is the energy of motion, and chemical energy, which is the stored energy waiting to be released by combustion. When the engine fires, that chemical energy is converted into the kinetic energy of the hot exhaust gases shooting out the back. But here's the clever part: the propellant is already moving along with the rocket. Its kinetic energy is not wasted. It contributes directly to the exhaust velocity. When the rocket is traveling faster, the propellant has a higher initial kinetic energy. Burning it at that high speed is like throwing a rock from a moving train. The rock's speed isn't just the speed of your arm, it's the speed of your arm plus the speed of the train. Similarly, the exhaust gas exits the rocket nozzle with a velocity that is the sum of its own expulsion speed and the rocket's current velocity. Because the change in the rocket's velocity depends on the speed of the exhaust relative to space, not just relative to the rocket, burning the fuel at a higher initial speed results in a more efficient transfer of momentum, giving the spacecraft a bigger boost for the same amount of fuel. The most powerful application of this effect occurs when a spacecraft is deep within a gravitational well, such as when it's making its closest approach or periapsis to a planet. This is the moment when the spacecraft is falling fastest, pulled to its highest velocity by the planet's gravity. From an energy perspective, the spacecraft has traded gravitational potential energy for kinetic energy, much like a roller coaster car accelerating as it plummets down a steep hill. The Oberth effect tells mission planners that this is the perfect moment to ignite the engines. By burning fuel when the spacecraft is at its absolute fastest, they capitalize on that extra kinetic energy inherent in the propellant. The chemical energy released by the burning fuel adds a fixed amount of energy to the system, but because kinetic energy increases with the square of velocity, adding that energy at a higher baseline speed results in a disproportionately larger increase in the spacecraft's overall velocity. It's a way of using a planet's gravity to temporarily loan the spacecraft extra kinetic energy, allowing the rocket engine to pay back that loan with immense interest in the form of a much more effective maneuver. A propulsive burn executed at periapsis can be several times more efficient than the exact same burn performed just a short time later, when the spacecraft has climbed away from the planet and slowed down. This is why mission plans for interplanetary probes are so meticulously choreographed around these close planetary encounters. We can see the Oberth effect in action in some of the most ambitious journeys our robotic explorers have ever undertaken. Consider a spacecraft on a mission to the outer solar system, like the Voyager probes. To reach the giant planets, they needed a tremendous velocity boost that their rockets alone could not provide. Their solution was a planetary flyby, a gravitational slingshot that is supercharged by the Oberth effect. As a spacecraft swings close to a planet like Jupiter, it falls into the planet's gravity well, accelerating to incredible speeds. At the precise moment of closest approach, when its velocity is at a maximum, the spacecraft might fire its engine for a critical course correction or an extra push. This burn, enhanced by the Oberth effect, can fine-tune its trajectory with minimal fuel expenditure, setting it on a perfect path to Saturn, Uranus, or beyond. The maneuver is a masterful combination of gravity assist and the Oberth effect, using the planet's pull both to accelerate the spacecraft and to position it for an ultra-efficient engine burn. This technique is not just for grand tours. It's also crucial for missions that require a large change in energy, such as slowing down to enter orbit around another world or, conversely, building up enough speed to escape the solar system entirely. The Oberth effect turns a planet into a cosmic launch pad, where gravity provides the runway and a well-timed burst from the engines provides the final, powerful kick. The implications of this principle even extend to visionary concepts for future spaceflight. Imagine a spacecraft designed to travel between stars. The energy required is so colossal that conventional chemical rockets are impractical. One theoretical solution is to use a powerful laser or matter-antimatter engine. To maximize its effect, you would want to ignite this engine at the point of highest velocity. Where might that be? The most extreme gravitational well in our solar system is the Sun itself. A hypothetical interstellar probe could first use planetary flybys to dive perilously close to the Sun. At perihelion, the point of its closest approach, the spacecraft would be moving at a staggering speed, perhaps hundreds of kilometers per second. Firing its immensely powerful engine at that exact moment would leverage the Oberth effect to its absolute limit, converting a huge amount of fuel into effective velocity and potentially accelerating the probe to a significant fraction of the speed of light. In this scenario, the Sun's gravity is no longer just an anchor holding us in place. It becomes the central component of an interstellar accelerator. The Oberth effect, therefore, is more than just a clever trick for saving propellant in our local neighborhood. It is a fundamental insight into the relationship between gravity, motion, and energy, a key that could one day unlock the gates to the stars, demonstrating that the same force that binds us to our world can also be harnessed as the most powerful propulsive aid imaginable. We have now journeyed through 24 profound unseen forces, from the cosmic scaffolding of dark matter to the subtle thermal nudges of the Yarkovsky effect. Each one is a piece in the intricate puzzle of the cosmos, a force confirmed by observation or strongly supported by our most robust theories. But our exploration would be incomplete if we did not cast our gaze toward the very edge of understanding, to ideas that are still speculative, waiting in the wings of science for their moment of validation or rejection. This brings us to our final and perhaps most theoretical unseen force, the concept of torsion fields, a potential twist in the fabric of reality itself. To grasp what torsion might represent, let's return to our most powerful description of gravity, Einstein's general relativity. In this magnificent theory, mass and energy tell spacetime how to curve, and that curvature tells objects how to move. We visualize this as a heavy ball sitting on a stretched rubber sheet, creating a depression that guides the path of marbles. This curvature explains orbits, gravitational lensing, and even the slowing of time. But what if that rubber sheet could do more than just curve? What if it could also twist? Imagine taking that sheet, and in addition to pressing a ball into it, you also try to wring it out like a wet towel, imparting a spiral deformation. This idea of a twisting, a rotational stress in the geometry of spacetime, is what physicists call torsion. In essence, if curvature is the response to mass and energy, torsion is proposed as the response to spin and angular momentum. The mathematics behind this idea extends Einstein's original equations. The theory that incorporates torsion is often called Einstein-Cartan theory, developed in the early 1920s by mathematician Eli Cartan. While Einstein's equations use a geometry that is Riemannian, dealing with curvature, the Einstein-Cartan theory uses a more general geometry that includes a property called torsion. In this framework, not only would a massive object like a star curve spacetime, but a spinning object, like a fundamental particle with intrinsic spin, would generate a tiny torsion field in the spacetime around it. This field would represent a twisting of the local coordinate grid, an additional layer of complexity in the gravitational interaction. It's a compelling thought. Every electron, every quark, every particle that spins might be imparting a minuscule, corkscrew-like distortion to the universe at the most fundamental level. So, why consider such an idea if it hasn't been confirmed? The potential implications are fascinating and could solve some deep puzzles. For one, torsion provides a possible geometric explanation for a property that we currently take as a given: the intrinsic spin of quantum particles. In standard physics, spin is just a quantum number. It has no classical analog, but in a theory with torsion, spin has a direct gravitational consequence. It twists spacetime. This offers a tantalizing bridge between the world of quantum mechanics and gravity, two pillars of physics that have so far resisted all attempts at a unified description. Furthermore, some cosmological models that include torsion suggest it could have played a role in the very early universe, potentially preventing the initial singularity of the Big Bang by introducing a repulsive force at extremely high densities, leading to a big bounce from a previous cosmic cycle instead of a creation from nothing. However, it is crucial to approach this idea with a clear understanding of its current status. Torsion fields remain a highly speculative concept. The effects predicted by the Einstein-Cartan theory are extraordinarily small, many orders of magnitude weaker than the effects of curvature, and far beyond our current ability to detect. No experiment to date has found evidence for torsion. It lives primarily in the realm of theoretical physics, a beautiful mathematical possibility that challenges us to think more deeply about the nature of space, time, and matter. Considering torsion and other ideas like it is not a departure from science but a vital part of its progress. It represents the frontier, the cutting edge where our known models are stretched to their limits and new possibilities are born. It is a humble reminder that our list of 25 unseen forces is not a closed book, but a living document. The cosmos is under no obligation to conform to our current understanding, and the greatest discoveries often lie in questioning what we think we already know. The dance of celestial bodies may yet be guided by forces we have not even begun to imagine, waiting for a future generation of scientists to pull back the next curtain and reveal a deeper, more wondrous layer of reality. And so we arrive at a breathtaking panoramic view. After this grand tour of 25 unseen forces, the cosmos no longer appears as a collection of separate phenomena governed by isolated rules. Instead, it reveals itself as an intricately woven tapestry where every thread is connected. The crushing grip of gravity that curves spacetime is the very same force that allows the subtle push of radiation pressure to balance a star. The ghostly scaffold of dark matter that sculpts galaxies also provides the gravitational wells where the violent ballet of galactic cannibalism, driven by dynamical friction, can unfold. The quantum fluctuations of the infant universe, stretched to cosmic scales, became the seeds for the majestic spiral arms of galaxies, whose rotation is subtly influenced by the Coriolis effect. This is not a universe of solitary actors, but of a deeply interconnected cast, each force playing its part in a continuous, dynamic performance. Consider the life cycle of a single star, a story told through the collaboration of many unseen conductors. It begins with a gene's instability, a critical threshold of density and temperature that causes a vast cloud of gas to collapse under its own gravity. As the protostar forms, the dynamo effect deep within its churning plasma generates a powerful magnetic field, which will later channel stellar winds and create sunspots. For billions of years, the star achieves stability, with the outward radiation pressure from fusion in its core perfectly balancing the inward pull of gravity. When it exhausts its fuel, its fate is sealed by the Chandrasekhar limit, a quantum boundary that dictates whether it will fade away as a white dwarf or explode in a supernova that seeds the galaxy with heavy elements. The shockwave from that very explosion then travels outwards, compressing nearby gas clouds and triggering a new round of star formation through the gene's instability, beginning the cycle anew. One star's death is another's birth, all orchestrated by an unseen symphony of forces. This interconnectedness extends to the largest scales imaginable. The dark energy that accelerates the expansion of the universe is fighting a cosmic tug of war with the gravitational pull of dark matter. In the early universe, dark matter gravity gathered the first clumps of ordinary matter, but dark energy now works to pull those structures apart over cosmic time. Within galaxy clusters, we see ram pressure stripping gas from spiral galaxies, quenching star formation and transforming them into ellipticals. Meanwhile, the Kozai mechanism orchestrates complex orbital dances in triple star systems, and gravitational waves ripple out from colliding black holes, carrying energy across the cosmos. Even the gentle, relentless spiral of a dust grain due to the Poynting-Robertson effect contributes to the accretion of material onto stars and the creation of the zodiacal light. There is no action, no matter how small or local, that does not ripple outward, influenced by and influencing the whole. To truly understand the cosmos, then, is to learn this language of interaction. It is to see that a planet's magnetic field, born from its rotating core, is not just a local shield but part of a conversation with the solar wind, which itself is accelerated by Alfvén waves traveling from the Sun's magnetic surface. It is to appreciate that the Oberth effect, a clever trick of orbital mechanics, allows us to harness a planet's gravity not as a barrier but as a partner in exploration. This perspective transforms our gaze from passive observation to active interpretation. When we look at the silent, starry sky, we are no longer seeing a static picture. We are witnessing a single frame in a dynamic movie, a moment in a dance where every participant, from the smallest asteroid to the largest galaxy cluster, is guided by a chorus of invisible forces. This symphony is the true language of the cosmos, a complex, beautiful, and unified composition that tells the story of everything. So as our journey comes to a close, we are left with a humbling and magnificent realization. The serene night sky, which has inspired poets and philosophers for millennia, is in truth the grandest stage imaginable, and the dance performed upon it is choreographed by a legion of invisible conductors. From the quantum seeds sown in the first instant of the Big Bang to the dark energy relentlessly stretching the fabric of spacetime, these 25 unseen forces are the true architects of our reality. They work in a silent, intricate concert, governing everything from the spin of an electron to the majestic swirl of a galaxy. This exploration reveals a universe that is not a collection of separate, mechanical parts, but a deeply interconnected and dynamic whole, a symphony of interactions where gravity's curve, light's gentle push, and spacetime's subtle twists are all verses in the same cosmic song. This understanding transforms our perspective forever. When you next look up at the stars, you will not see mere points of light against a black canvas. You will perceive the ghostly grip of dark matter holding those stars in their swift orbits. You will sense the silent stream of the solar wind brushing against our planet's magnetic shield. You will feel the faint tremor of gravitational waves, ripples from collisions that occurred billions of years ago. The cosmos is alive with invisible activity, a place of profound mystery where elegance and order emerge from the interplay of forces we are only beginning to comprehend. This knowledge does not diminish the wonder, it deepens it, inviting us to see the universe not as a passive picture, but as an ongoing, dynamic story. And the most thrilling part of this story is that the final chapter has not been written. Our list of 25 is not a closed book but a living document, a testament to human curiosity and our relentless drive to uncover the secrets of the cosmos. Who knows what other invisible conductors remain waiting in the shadows of our understanding? Perhaps a deeper nature of dark energy, a clearer picture of the quantum vacuum, or even a completely new force that will redefine our place in the universe. The instruments we use to probe these mysteries, telescopes that see in gravitational waves, detectors that hunt for dark matter particles, and theories that push the boundaries of physics, are becoming more powerful with each passing year. The dance continues, and we are only just learning the steps. We want to hear from you. Which of these unseen forces captures your imagination the most? Was it the ghostly presence of dark matter, the mind-bending reality of gravitational waves, or the subtle thermal nudge that steers asteroids? Share your thoughts in the comments below, and if this journey through the hidden architecture of the universe has sparked your curiosity, be sure to subscribe. Our exploration of the cosmos is far from over, and we look forward to continuing this incredible voyage of